Hello, this is Jason Kendall and welcome to the next of my introductory astronomy lectures. This time we're beginning the path to talk about telescopes. Telescopes are our window into the cosmos, and they're our way of measuring things about from light, of the light, from distant stars, distant galaxies, nearby and far planets. So this is how we get all of our information, and we use these telescopes to observe the light. So let's see how a telescope works. I'm going to have a series of videos along this, about 3 or 4 videos talking about the nature of telescopes. And this is the first one. So an elementary telescope is a very basic idea. You can take 2 lenses, each with different focal lengths, and put them in front of your eye. And the first one will gather a bunch of light, bring it to a focus, then as it spreads from that focus, you can put a magnifying lens very close to your eye that will then take those and spread them out and collimate them into your eye to magnify the image. So an elementary telescope, a very elementary telescope, consists of 2 lenses, one of which is the primary or the objective lens, and the other one is the magnifying lens. In effect, you're basically doing your eyeglasses, put one in front of the other, and then you attach them to a tube. So the refracting telescope was one of the first telescopes built, and it was the thing that started Galileo along. So the front lens we'll always call the objective or the primary, and sometimes if it's a mirror is the thing that intercepts the light first, we'll call that the objective or primary mirror. So how do these lenses work for a refracting telescope? Well, they operate by the process known as refraction. Refraction is simply what you observe when you see light going into a medium from one medium, say air, into a different medium, say water, say reflecting off of that, and then coming back to you outside of that medium. So when we talk about medium, we're talking the thing in which light is currently traveling. If you're looking at interstellar space, the medium is a vacuum. If you're looking in the air, like we're breathing and walking around in, the medium is air in which light is traveling. Sometimes it travels in water, sometimes it travels through solid brick, but that would be for radio waves. But sometimes you want to make it travel through lucite or any other transparent medium so that light can go through it. Visible light specifically. It's not transparent, you're not going to see through it. So we're going to think about things like water and glass for their refractive capabilities. Well, what is refraction? Refraction is the apparent and measurable change in direction of the path of light as it traverses from, say, air to water, or from water to air, or something like that. So when you build a prism, the most basic idea is that you build a prism, which is a very pure piece of glass where the surfaces are polished very smoothly, and a prism can be triangular in shape, and that's the typical thing you'll find at like a gift shop at a museum, and that one side is flat, all 3 sides of a triangle are made as flat as possible, and you have light coming into the prism, going through the prism, and out the prism. In this diagram I'm showing you, we have the 3 sides of the prism, and then there's a red dashed line. That red dashed line is what we're going to call the normal. The normal is a line, an imaginary line that sits on the top of, that sits perpendicular to the surface of, say, the prism. So the red line is perpendicular to the surface of the prism, and it's not a real line, but it's an imaginary line. So we can then say, the light is coming in with some angle with respect to the normal, and then it goes into the prism, and that normal can be thought of as being extended into the prism as well, and we see that this light is bending towards the normal. So makes it a bigger angle in air than it is in glass. And then it travels through the glass and gets to the other side of the prism, and there's a large angle, and that large angle is made even greater because when you go from a dense medium like glass to a less dense medium like air, it pulls away from the normal. So we see that the path of light, by traveling from, we see, and as made evident by the path of light being changed by the presence of it going into the glass. Well, this is an interesting thing. We looked at yellow light. What about red light? If we look at red light, we see the bending of the path is not as great. And if we look at blue light for air and glass, we see that it's actually even greater bending of light. And if we put them together and compare them side by side, we see that as you progress from long wavelength, red visible light, to shorter wavelength, blue visible light, we see that it acts to effect to spread the colors out. And if we then think about them as all being part of a white ray of light, which is just an unbroken ray of light, then as it goes from an unbroken set of light, a mix of all the light, goes into the glass then separates them out, and when they go back to air, it separates them out even further. So this separation happens because the speed of light itself is different inside of glass than it is inside of air. And the speed of light is also dependent on frequency. Otherwise, the red light and the yellow light and the blue light would all get the same bending. So this refraction index, we can call it, say, well, what is the index of refraction? The index of refraction is dependent on the wavelength of the light that's coming into it, and it's also dependent on the material from which in which you're traveling. So a while back, Snell's law of refraction was created, was observed, and we see, okay, for a given index of refraction, say air, another given index of refraction, say glass, we can measure what those indices of refraction are, and we find that there's a relationship between the index of refraction and the angle with which we measure it from the incident light with respect to the normal of the surface. So there's an interesting little relationship between them, and I'm just going to describe it because I've got it right here, so I better describe it. So we have the index of refraction of, say, medium 1, which might be, say, air, and that is wavelength dependent. That's what that lambda means, and it's multiplied by the sine of the angle of incidence, which is theta sub 1. So if we take the index of refraction of air, number 1, medium, which is wavelength dependent, and multiply it by the angle of incidence that it has with respect to the normal of the surface of, say, some water, then that will be equal to the index of refraction of, say, water, which is also wavelength dependent, times the sine of the angle of that has been refracted, so which is inside of medium 2, which is here water. So we have index of refraction 2, which is wavelength dependent, and the sine of the angle of refraction into the medium as it passes from air into water. We change media, so we change indices of refraction. And you'll notice that from this particular example, the index of refraction bends the light towards the normal as it goes from air to water. Now, what exactly is the index of refraction? It is defined, that's what that triple dash means, the index of refraction as a function of wavelength, which is the letter n, which is the index of refraction, sub lambda, which means that's the wavelength dependence of the index of refraction. It's defined to be the speed of light in a vacuum divided by the speed of light at a given wavelength in that medium. So the index of refraction is a weak function of wavelength in air and water for visible light. It tends to be rather smooth, the index of refraction function. So I'm not going to put the index of refraction functions up because, you know what, they're a little hairy, and they can be extremely hairy depending on the type of material that you're looking at. But for something simple like air or water or glass, or even more specific kinds of glass like fluorite, the wavelength dependence is rather smooth, and you can actually find them online or work with them if you're doing material science with glass. So refraction is a very common thing, and we define Snell's law of refraction as the relationship between the angle of incidence and the angle of refraction given the two indices of refraction of the two media. All right, so in addition to the indices of refraction having an effect, the geometry with which you have the incident light come in plays into effect as well. So if you have a glass prism that's really fat and thick, then the angle of incidence can be very steep as it comes in. And so that would make a much larger deflection angle as it goes out. But if you have a very, very thin lens, then the deflection angle as it passes from air to the glass back to air can be very small. And we can use the geometry of this to our effect. In fact, notice the glass prisms up to this point have always had one flat side. But we know that we can shape glass. And eyeglass and optometrists all across the world use the fact of refraction to help you see better. So we can make lenses, say, for eyeglasses in a rather simple way. if we bend or make a curve to the glass, not a flat surface, but a curve, then we can focus the light. And so a lens maker will take a piece of glass that's maybe a flat, like rectangular block, and they'll polish or sand the sides down so that the one side has a curvature to it. And what is that curvature? It would be the curvature of, say, a sphere. And so you grind it down until it has a curvature of a sphere. And what is the radius? And so spheres can be really small, like a little BB, or they can be really big, like something you can hold in your hands, like a beach ball, or even something really huge, like the sphere at the American Museum of Natural History, the Hayden sphere, which is 30 meters in diameter. So, but let's say we have a very small, we can have a long curvature for the thing, which would mean that they would look like a long radius of curvature would make the lens very flat. But if it's a short radius of curvature, it would make the lens really round. So depending on the shape that you wish to make it, the curvature of the lens, it can be a spherical lens. We could do other kinds of shapes, but let's keep spherical in just for now because that's a little easier to work with. So if you make one side of the lens have a curvature radius, so you have a radius of curvature, maybe this is the point, and you make a swing or arm around like this, that's the radius of curvature. And you just mark off, you sand down the glass so that it has, from a flat surface, down to that curved surface, or the one radius of curvature. Now maybe the other side is a little different. Maybe you want a stronger curvature, so you make a shorter radius of curvature, and so you have a much rounder edge. So then what we can say, well, if we have these two surfaces, one kind of flat and one kind of really round, this will bring the light to some focus. And how does that work? Well, we know the index of refraction of glass, so we know it changes the direction of the glass, but the lens maker, an optometrist who's making the lenses for your eyeglasses, and if he's using spherical curvature to make the lens, then he'll say, okay, what's the radius of curvature of one of the sides and the radius of curvature of the other of the sides, take the reciprocal of the two, add that together, multiply it by the index of refraction of glass, subtract 1 from it, and that's equal to the focal length that it's brought to. So the light comes in as nice straight lines, and because it goes in one curved surface and out another curved surface, that brings the light to a focus. And that's how lenses work. You have two curved surfaces, it brings them both to a focus, and then we have a focal length to the lens. So every lens is characterized by its focal length, more specifically from the center of the lens to a point where all the light rays converge as a result of the refraction of the light through the lens. Okay, now here's a funny thing about those lenses is that because the index of refraction, as we saw from the Pink Floyd album cover and from prisms, that the index of refraction is wavelength dependent. So if you do have eyeglasses, you do have a thing called chromatic aberration, meaning where red wavelengths of light is focused differently than where blue wavelengths of light are focused and where green wavelengths of light are focused. Those places have different focal points. So you can't, it's very difficult to actually correct for chromatic aberration. You have to use lots of lenses, maybe use different materials, maybe you have a gradation of material inside of the lens, maybe you put special coatings on the lens. So it's an enormous battle with lens makers to eliminate chromatic aberration, especially for telescope makers that are making refracting telescopes. So chromatic aberration is part of the deal that you get when you use a lens to focus light. So what might be better than that? Well, if you want to make a very large telescope, you really can't make a big piece of glass that's like 6 feet in diameter, because that's a huge piece of glass. It has to be a perfect piece of glass because all the light's got to go through it. It's got to be held at the edges so that you can have this warping of the glass, and that can be a big problem. So maybe what we'll do is we'll reflect something off of a surface. And that's another property of light, is that it reflects off of a surface. So if you have a shiny surface, the angle of incidence equals the angle of reflection for a shiny surface. And we can use that to our advantage too, because initially we think of things like a flat surface, like a flat shiny surface, and we see a coherent image. But if you make the shiny surface curved, then you can change where the light goes. So if we use a curved mirror, we can focus the light by bouncing the straight light rays coming in, and then if you use a parabolic shape, you can focus all the light to a single point that's in front of it. You can use spherical as well, but then the edges of it don't focus exactly where you want them to. especially for the incoming light rays that come in very steeply. So we typically use a parabolic shape in order to do telescopic mirrors to focus it all at one point, because that's kind of the definition of a parabola. Straight lines come in, they all go to the focal point of the parabola. All right, so this is another way that we can focus light. There are two ways we do so. We know and no matter what, from the center, we can either use a lens to focus light because of the curvature of the surface of the lens and the refractive index of light passing through the lens, or we can change the shape of a mirror and focus it to a point. In any event, the focal length of the mirror or the lens is a key measure of the instrument itself. And so next time, we'll talk about how we'll use these focal lengths in order to create telescopes. Doing more on the fundamentals of telescopes. So here we go. The most important aspects about telescopes are their ability to discern things. And so the ability to discern things is related to what we call resolving power or resolution capacity. So we can see in this very funny little picture taken by someone at the European Southern Observatory that this baby might be much larger than a 5-meter telescope, or a very large telescope at the European Southern Observatory. But we know that babies don't come in the sizes of incredibly large telescopes, so we must be doing something with angular size, and we must be doing something with resolution. So the angular size of an object is something we really got to look at and understand. And the angular size is not the physical size. The angular size is how big something looks, and it's just how big it looks. But that's dependent both on its actual size and its proximity. So let's go back to our 10th grade or 5th grade algebra class or trigonometry class, and we actually take this definition of an angular measurement called the tangent. And the tangent of an angle for a right triangle is simply the size of the object, when we're looking at a right triangle, the size of an object compared to its distance. So the tangent of the angle is, assume something standing straight up and down, and how far away it is from you. The tangent of the angle from the bottom to the top of that thing is the size that we perceive it to be, is the size of the thing divided by its distance. The tangent of the angle that subtends is equal to that distance, that ratio. So what do we mean by that angle then? And we're going to really play around with this thing, because the angle that theta angle, the Greek letter theta, is very important to us. All right, so the tangent of an angle may be thought of in that original way, which is the distance to the object. Maybe it's a flagpole, maybe it's a tree, maybe it's a really, really, really large object. But if it's close, the angle will be large. And if it's far, the angle will be tiny. So let's actually look really carefully at this thing for just a second, and where do we get tangents from and all that kind of stuff. So first, if you look at this diagram carefully I've got here, the diagram itself, it inscribes a circle. So we've got the radius from the center of the circle to the circle, that's called the radius, of course. And we can take one radius here, and then we swing the radius up, and we have an angle that is taken out of the circle. Now, the tangent of that angle is a piece of the radius, not the entire radius, but a piece of the radius, which I've here described as a dashed blue line. So that's the distance to the base of it. Now then, we can then go from that dashed blue line up to the circle, and then the hypotenuse is the radius. So we've got the adjacent, which is a segment that's adjacent to the angle. We've got the length of the segment that's opposite the angle, and then we've got the hypotenuse. So these are all trigonometry, which is all based on angles around circles and right angles. So the right angle is between the opposite and the adjacent, and the hypotenuse is the radius of the circle. So the tangent of the angle theta is related to circles. So let's let now this angle theta let's define two other things before we do that. The first one is, let's say, okay, so the two radii for the angle theta touch the circle at two places. And so we may look at that as a length across from the place where the two radii touch, and that's the green line. That's like a straight line, so it almost looks like an equilateral triangle, but it's where the two radii touch the circle. And then we can look at the actual chord on the circle, which is the red line that is on the circle itself. So these three things are three separate lengths. Now, what happens if we let the angle theta get really, really small? Well, the dashed line gets really close to being the entire radius. The hypotenuse is always the same. The apparent height looks smaller and smaller and smaller, and the blue line going from the bottom radius up to the other one gets really close in size to the green line. And it also gets really close in size to the red chord going on the circle itself. So the blue vertical line, the green cut, and the red chord all get very close to each other's lengths as the angle theta gets smaller and smaller and smaller. All right, so now we're going to define the concept of a radian. And a radian is simply take the radius of a circle and put it on the circle. So we've got the radius, so what is that angle? We can define the radian as an angular measurement. We tend to think in terms of angles as like 360 degrees around a circle, but we could instead say, what is the angle subtended by the radius on the circle? And that's always the same for everything. For every circle, it's always that same thing. So we take the radius of the circle and we put it on the circle, and that subtends some angle, and we define that to be 1 radian. All right, well, that's a pretty big angle. It's pretty close to 60 degrees because there are 2 pi radians around a circle. All right, so if 2 pi radians is the same as 360 degrees, but we want to go look at really small angles. So we know there's 60 arc minutes in 1 degree from our way first episode, and we know there's 60 arc seconds in 1 arc minute. So how many arc seconds are there in a radian? There are 206,265, and we saw that before when we were talking about parallax. So this is kind of a redo of parallax for just a second. But we could say there are 206,000 arc seconds in 1 radian. Well, let's make our angle so small that we're only measuring it in individual arc seconds or even arc minutes. Those are really small amounts. So if we measure our angles in arc seconds or arc minutes, then the angle that's subtended is really tiny, and the green line that's on this diagram is very close to the red chord. And so you can almost not tell them apart. Once we get to that size, then actually when we have very, 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 very tiny angles, then we can approximate the length of the chord to being the actual physical size of it, which is the length of the chord is the physical size. And that physical size at some distance is the approximation we're looking at is equal to that the angle in radians. So the physical size divided by the physical distance, and we're approximating the physical size, which is actually straight, but we're approximating it by a really narrow, tiny curved surface, which is the red line here. So again, the angle in radians, which is really small, can be approximated by the size divided by the distance. So the tangent of an angle, when it's really small, is approximately the angle itself, so long as we're measuring in radians. Okay, so how does this work out and what can we use it for? So let's say we have the angular size of something. Pretend we're looking at a football. A football is about 12 inches across. Strictly speaking, it's about 11. And if we take that football and we pushed it so far away that it's about 1 arc second in size, then it's 39 miles away. That's really tiny size. That looks really small. So that has a small angular size. When something looks small, but you know it isn't small, we know the angular size is small. Now, if we took a football and brought it straight in front of your face, it would have a large angular size. That doesn't change the physical size of the football. It changes your perception of it, how big it appears to you. So the bigness appearing to you is what we call the angular size. The actual physical size and how big it appears to you depends on how far away it is from you and how big it actually is. So to make a football have an angular size of 180 degrees, it needs to be so close to your face that it fills up your entire vision. And that's the angle. But then we can't use the small angle formula anymore, and that doesn't work. So we really care about things that are really far away, because stars are very far away. So that helps us. In this sense, then, a football, which is about a foot across, placed 39 miles away, will be and have an angular size of 1 arc second. All right. So let's see, we're going to look at that for just a second. So angular size, we're going to put that aside for a second and look at the nature of what we call resolving power. So telescopes have, one of the key characteristics of any telescope is actually to be able to resolve things. We want to make out a star from a planet, or we want to see the curlicues of the gas inside of a gas cloud, or we want to make out one star cluster from another in a distant galaxy, that kind of thing. So that's called resolving power. We want to resolve two things that are separate, that are known to be separate, but if they're not resolved, then they're smeared together. So let's see what that works out to be. So resolving power is one of the most important things, and it is limited because once you send, because of diffraction, because the way light diffracts through a boundary, once you send it through some opening, light starts to diffract, and it makes it less smooth. So we can have all this light coming for light years from this distant thing, and it's all undiffracted. As soon as it goes through the aperture of a telescope, it starts to diffract around the boundaries of the aperture of the telescope. That even happens when you hit it off you don't even have a tube for the mirror like research telescopes, and just hits off the mirror itself. The physical size of the mirror itself then starts the diffraction process. All right. So let's look at some examples, and we're going to look at something that's like 10 arc seconds, 10 arc minutes, 1 arc minute, 5 arc seconds, and maybe 1 arc second resolution. And I'm going to play around a little bit here just to give you kind of a feel for it. And I took some images. I took an image of the Galaxy M31 with iTelescope. It's a wonderful service that's a paid telescope service, so if you want to go investigate, please do. And what I did is I then pretended that the resolution was only 10 arc minutes. And that's about what you see with your naked eye. So if you were to look up in the sky at the Andromeda Galaxy, and it's a really dark night, you'd see a fuzzy patch in the sky. And what you're seeing on the screen here is that kind of resolution, as bad as your eye can be. Now we're going to go to 1 arc minute resolution. It's slightly better resolution, and that might be what you get with a good pair of binoculars. Okay, so now let's bring it down again. And if we have 5 arc second resolution, 5 arc second resolution is about 12 times better than 1 arc minute resolution. So now we're deep into much better than what you can see with your eye, and we're starting to make out smaller and smaller features. They're not so smooshed together. And finally, when we get to 1 arc second resolution, which is really good, and really good. I don't even know if this is actually 1 arc second resolution, but I'm pretending that it is just for example purposes. Now we can distinguish gas clouds inside of the Andromeda Galaxy. We can distinguish distant stars that are still in the Milky Way. We can see faint things that don't get blended in with other things. So the resolution of an object allows us to separate things. So if we start again from 10-minute arc second resolution, it's really fuzzy, and then when we get down to 1 arc second resolution, it becomes much clearer, and things that are closer together are separated. All right, so that resolution happens because as light goes into an aperture, it diffracts. So the larger your aperture, the less the effect of this diffraction. But diffraction limits the resolution of all telescopes. It doesn't matter what they are, whether they're Hubble Space Telescope, some big telescope, some little telescope. Diffraction is the limit to the telescope. So what is this diffraction limit? And it's because if you have a telescope with a circular aperture, you get rings around an object. You get a bright central peak and then rings that surround it. And these rings are called Airy disks. And the Airy disk is, of course, named after Sir George Airy, who discovered it and modeled it mathematically. Well, he didn't discover it. He modeled it correctly mathematically in 1835. So let's say that you have 2 stars and they're coming in you want to distinguish them because maybe they're a really cool binary star that are orbiting each other, and you want to really see their orbital motion. So you want to distinguish these 2 binary stars. So when the light from the two stars enters your telescope, the circular aperture of the telescope, it starts to make these airy disks. It creates them by the time it gets to your detector. You can't do anything about it. You've got the airy disk of the two stars. Well, let's hope they're far apart, because if the two stars are not far apart, then you can't distinguish them. The best you can do is when the peaks are outside from each other and the first ring of the airy disk overlaps the edge of the center of the airy disk of the peak of the other. So the first ring of the airy disk goes across the bright central peak of the other one. And so that's just being able to tell the two apart. And if you look at this diagram, we have three different flavors of that where there is some darkness between them. The other two do not show any darkness between them. So you can't tell if it's two stars or if it's like an oblong peanut-shaped object. So when the two airy disks overlap, that's when you're getting what's called the diffraction limit. So the diffraction limit for a telescope is kind of an arbitrary definition. I mean, you could play with it in order to get a better resolution. You could pretend that on this diagram that you see here, that the middle one is actually two stars, but you really wouldn't be able to be sure. So we're going to call this thing the diffraction limit, and it'll be specifically the Rayleigh criterion. And the Rayleigh criterion is this: the angular separation that you see them to be, which is theta, is equal to 1.22 times the wavelength of light that you're using divided by the diameter of the telescope you're using. And we're assuming a circular aperture to your telescope. And the 1.22 comes as a result of it being a circular aperture and creating rings. Now, if we had a flat slit or a box of some kind, it would be a different number out front. But telescopes tend to be circular, so therefore we get a 1.22 there. And the key is that the wavelength of light is dependent. So short wavelength means smaller, where you can resolve smaller smaller angles. If you have a bigger diameter, then the number is smaller also. So you want to look at short wavelengths and big diameters and use a big diameter telescope in order to get to your diffraction limit. All right, so for as an example, the Hubble Space Telescope, it's up in space. It can look at visible wavelengths, so a typical bluish sort of greenish visible wavelength is about 500 nanometers. The diameter of the Hubble Space Telescope is 2.1 meters. So therefore, if we plug it into this Rayleigh criterion equation, we get that the angular size, the diffraction limit, is about 3 times 10 to the minus 7th radians. Remember from the beginning, we're looking at really small angles, so this is good. And that means about 0.06 arc seconds. So the Hubble Space Telescope's diffraction limit is 0.06 arc seconds. So if something is, say, 0.01 arc seconds or 0.0001 arc seconds, the Hubble Space Telescope isn't going to be able to resolve it. So if we then say, let's play around with it and say, let's say we could point the Hubble Space Telescope at the moon to try to see the flags left by the Apollo missions. All right. The moon's about 2,000 miles across, it's about a half a degree wide, so therefore that's 1,800 arc seconds in the sky. And since it's 2,000 miles across, in 1,800 arc seconds, that means the Hubble could, in theory, resolve something as small as about 330 feet apart because of diffraction limit. All right. The flags of the Apollo mission are about 4 or 5 feet wide, so we're never going to resolve the flags from using the Hubble Space Telescope. Also, if you were to mention this to John Grunsfeld or anybody else on who deals with the Hubble Space Telescope, or Mike Massimino, who's this really big guy over at the Intrepid Air and Space Museum, who's actually done Hubble servicing missions, he would want to throttle you, because if you pointed the Hubble Space Telescope at the moon, you'd blow out the instruments, because the instruments are incredibly sensitive and designed for low light, not for the brightness of the moon. So we can't see the flags on the surface of the moon even using the powerful Hubble Space Telescope, because the diameter of the Hubble Space Telescope simply isn't big enough in order to get the resolution we're looking for. All right, so we can't do that, and what's even worse is that let's say we took the Hubble Space Telescope and instead, well, there's 2-meter telescopes on the ground, right? You can build a 2-meter diameter meter and a 2-meter diameter telescope on the ground and point it at things, but you will never get 0.06 arc seconds on the ground. And that's because at best on the ground, we get about 1 arc second from the ground. And why is that? It's because we got the air. The air, we talked about this last time with the refraction of air. When light goes from a vacuum into air, it starts to refract. But yet the air is turbulent, meaning that there's pockets that have a little bit more water vapor, a little less water vapor. They might be drier, they might have a different temperature. So that changes the index of refraction of the air, and these sizes of these bubbles in the atmosphere range from about the size of about a basketball to the size of a car or so. And so the sizes mean that as the light travels through the atmosphere from a distant star, it's been going in a straight line for light years, maybe 1,000 light years, say for star Betelgeuse, 600 light years. It comes in the atmosphere and then starts to refract and bend, and its path changes as it travels through the brief bit through the atmosphere to come to your telescope. And that makes the star's image wander, and that's where the twinkling of stars comes from. Because as the image wanders, if you're looking at stars without a telescope, the starlight comes into your eye and falls in between the detectors, which are called the cells of your retina. And so you see a twinkling in your eye. Now, in a telescope, we don't really care about that because we have a detector, and the detector has pixels. And so it wanders around on the surface of the pixels, spreading the image. So if we look at through a telescope with a detector or a camera, the image spreads on the surface because of the variable refraction that the atmosphere has as the light's coming to us. And we call that spreading of the image seeing. And if seeing is bad, meaning it's kind of turbulent, there's lots of moisture in the air, there's clouds in the sky, maybe there's high clouds, so that would be the seeing is bad and it looks schmutzy. Yeah, you might be able to see some stars through a very thin cloud layer, but you wouldn't want to try to take detailed images of some faint star cluster or some faint nebula, because it'll be out of focus. Why will it be out of focus? It'll have poor resolution. Why will it have poor resolution? Because the seeing is bad from the index of refraction changing through the sky. So as we've seen, the resolution is our big thing. It depends upon the angle that we're looking at, and typically the size scales, the angular size scales, are less than a few arc minutes that we care about, and maybe we're looking at something that we're looking at for arc seconds. And so angular resolution is really key. The only way we can get better angular resolution is building bigger telescopes. If we build bigger telescopes, we better build them in space, because if we don't build them in space, we have to contend with the atmosphere on the ground. And that's called seeing, and that is not a diffraction limit, it is an atmospheric limit. Now there are strategies to get around this, and we will look at those next time. See you. We're going to finish off the basics of telescopes this time, and we're going to talk about some of the aspects of things that you probably do know or might not know about the nature of what a telescope is and does. Well, first let's go with the more interesting things that you see. Let's say you go to an amateur observing telescope party and you look through a telescope and you see the moon in the sky, and it might be a crescent moon. But in the telescope, its image is inverted so that the crescent faces the other direction. And the craters seem to be upside down too. Well, that's because a telescope will invert an image and flip it as it passes through the light path. Now, one way to think about that is the light comes from the moon, let's say, and goes into a lens, say of a refractor. It goes into the refractor's lens, it goes to a focus, then it starts to broaden out again from the focus, meaning the upper light, the light from the top of the moon, gets swapped with the light from the bottom of the moon. Then as it starts to diverge again, you put a magnification eyepiece right there so that it sends it to your eye. So the magnification is you would have a magnifying eyepiece, and then the inverted mostly it's because as the light comes through, it gets inverted, and then the eyepiece then rectifies it and focuses it to your eye. So all telescopes that we look at invert the view. In fact, your eye as a lens inverts the view, but your brain then re-inverts those views so that you see the world right side up rather than upside down. But your eye as a lens actually flips the view of the world, because that's just what lenses do. So when it comes to a mirror, though, the mirror image then, when you have a mirror image, you have to rectify that as well. Mostly you just figure out which way is up and which way is down, which way is north, east, and south on the plate, and then you can fix that in Adobe Photoshop later, or using IRAF or some other, or Python IRAF or PyRAF or something in order to deal with the actual orientation of the image after the fact. But that's why when you look at a telescope, you always see it upside down and backwards, and that's because of the path of the light through the telescope changes the orientation. All right. But more important than the orientation is a characteristic of a telescope called the focal ratio. The focal ratio is a primary characteristic of every telescope's design. It's defined to be the focal length of the objective, or primary, divided by the diameter of the focal length of the diameter of the primary or objective. So that's called the focal ratio. The focal length divided by the diameter. One of my telescopes that I own has an 85 millimeter diameter and has a focal length of 600 millimeters, and so I'll call that a focal ratio of 7, or an f7 telescope. And that's just a little refractor I have, and I really like it. But the focal ratio can be called the speed of the telescope. So the smaller the f number, what they call f slash, when you see that diagram, when you see it on a telescope, what's the focal ratio, what's the f number? The focal ratio, the f number, the smaller the focal ratio number, the lower the magnification, the wider the field of view, and the brighter the image is with any given eyepiece or camera. So a short focal ratio are good for good for observing wide fields of view and deep space photography, deep space astrophotography. But if you have a slow focal length, meaning typically a slow focal ratio means the focal length is very long. And those are usually better suited to high power lunar or planetary observing and binary observing where you want to get high powers. So if you want to do something in the middle, like say an F5 system, or just comparing two systems, if you compare an F5 system to an F10 system, what that means is that for a given diameter, if it's the same diameter, or even a different diameter, the focal image will be, essentially, you'll be able to, for a given F5 system, we'll be able to image or an extended object, specifically an extended object like a nebula, in a much quicker time, about a quarter of the time, but it will only be half as large an image at your detector. It's an interesting thing to have. So point sources, though, like stars, they don't really care about that. It's primarily, we're only caring right now at this moment to extended objects, but point sources like stars, they care more about the aperture because you're just trying to collect photons from a point source. But for a focal ratio, that's what we're talking about, getting spread out, getting brighter and dimmer. And that's what we call the plate scale. So the focal length of an object determines its plate scale. The plate scale says how big is your image at the prime focus. When you focus all your light at that place, so the light goes through the lens, it gets focused down to a point, how big is the image at that place? It started this big, how big is it now at that point? So we'd have to say that the image is smaller in area than the object collecting the light. Here comes the big, it comes in, it hits a big mirror, and then it gets reduced down in size in terms of actual areas, in terms of physical area, to a little bitty tiny thing. The longer the focal length it is, the bigger the physical separation of points are on the detector. So that's kind of a weird way of thinking about it. But that's kind of what you want. So let's say you want to image Saturn's rings and get all sorts of beautiful things and beautiful details. Then you want a large physical separation of the individual ring diameters, like the Cassini division, on the detector so you can make them out. So you want a very long focal length in order to get a large physical separation. And what do we mean by physical separation? We're not talking about the rings of Saturn themselves. We're talking about physical separation of points of light or sources of light on the detector. Because remember, your detector is a physical thing. It is like it's a camera. The camera has some sort of detector on it. So as the light comes through the detector, it focuses it down to a physical location. You put your image detector at that physical location. So you're going to have a larger physical separation, but you're going to have a smaller image. You're going to see less of the object, but everything you have on the detector will be spread apart bigger. That's a good way of thinking about it. Another way of thinking about it is if you have a really long focal length, it's like looking down a tube with no lens, right? So you're just saying, oh, I want the whole thing, but then the detector then looks at a specific little area. All right, another way of looking at it is the plate scale can be measured in terms of arc seconds of the sky per millimeter of the detector. That's another way of looking at it. So you're going to say how many arc seconds are there present on this diameter of the detector per millimeter of detector. Your detector could be this big or this big or that big or this big. We want to know per millimeter on the detector how many arc seconds there are. And that's called the plate scale. It's dependent on the focal length. So the plate scale, you get more arc seconds per millimeter with a longer focal length. And you get with a shorter focal length. The shorter the focal length, the more arc seconds you get per millimeter. That makes a big field. So if you want to really zoom in, you want to get a high magnification, then you want to have a long focal length, which gives a shorter plate scale. All right, so the other thing that kind of leads to is the concept of magnification. Now, when you go to a junk store and you want to find, you go into like some discount department store, and they've got over here in the children's section a telescope made by cheapotelescopes.com. Cheapotelescopes.com will have a big thing on the box that says, well, this is a 100 magnification telescope. Never buy a telescope based on magnification, because magnification is the least important thing. The focal ratio is important, the aperture is important, whether or not it's got a steady tripod is really important, whether or not it's actually got, steel eyepieces or plastic eyepieces, that's more important. Never buy a telescope by the 100 times magnification on a box in something in a store somewhere. I know I'm preaching to the choir here, but hey, you got to tell somebody, and somebody's going to see this. You can say, don't bother with that. Go actually look for a real telescope. But what actually is magnification? Magnification is the apparent change in angular size that you see an object to be because of the effect of the eyepiece. So the magnification is the focal length of the objective divided by the focal length of the eyepiece. So if you have a primary length, like in this example, we could say that the focal length of the primary is about 60 centimeters, and the focal length of the eyepiece maybe is 3.7 millimeters, then you're going to have a magnification of 161 times. So if you have a really short eyepiece really short eyepiece focal length, then the magnification is going to blow up and be really big for a given objective, for a given focal length of an objective. Most telescope makers would say don't bother with a magnification greater than 200, because as you magnify, you spread the light out over a larger and larger area, so therefore the image gets dimmer and dimmer. So higher magnification means a dimmer look at the thing. It doesn't make it brighter, it makes it dimmer to your eye. If you want to make it bright, make low magnification. That makes it very bright. The greater the magnification, the dimmer it is, because you're taking that and spreading the light instead of having it into a little area, it's spreading out into a large area. So it's an interesting way of putting at it. And the more, as you're buying telescopes, look at magnification dead last. In fact, don't even bother considering it. You want to consider the quality of manufacture and the diameter of the telescope and the focal ratio. That's the things you care about. And maybe even what you want to do. You want to look at the planets, you want to look at deep space. But typically there's always a balanced sort of thing, a middle road focal ratio that'll get you there. And those things are for another day of talking about it. All right, so what kind of telescopes do we have out there on the market that exist in the world? Well, modern research-grade telescopes and large purpose telescopes are all reflectors. There are no major research-grade refractors left, because that's a big piece of glass. And a big piece of glass, let's say you have a 3-foot diameter piece of glass. Now, that's going to have a long focal length. So that means you're going to put this in a very long telescope. And a long telescope has a big lever arm, which means that the telescope itself would weigh an enormous amount just to support the glass. And then the glass has to be supported at the edges, not in the middle. So you have only one edge to support it. Also, the lens has to be really perfect. So as you look at it, you go, wow, this is kind of a crazy thing. If I'm going to I get some really nice views with a refractor, which is true. You can get some extraordinary views with a refractor. but it's not going to be a research quality because you need to have something bigger, you need to have brighter, and you need to have higher resolution. And that means a reflecting telescope. So the reason you don't use refractors for research is that you got to have really perfect glass, you have to have a really perfect surface, and it has to be supported in ways that are really difficult and extremely expensive to do. So elementary reflecting telescopes, there's lots of different kinds of reflecting telescopes. So the basic is you've got a mirror, and then you put something, you figure out a way to put your detector at the prime focus or at the focal length. The problem with reflectors is, of course, you gotta put something in the path of the light. So you get diffraction, not just from the telescope, but diffraction around the thing that you've put to gather the light with. So a Newtonian telescope, which is a standard thing you'll find for sale from lots of different telescope makers, you put a secondary mirror that's held by some struts and that sends it out the side of the tube, and then you put an eyepiece there. All right, so now you've got diffraction not just from the blocking of the mirror, but from the struts that hold the little secondary mirror in place. Yeah, and people that really like to do very high quality imaging, they try to use refractors, but they're small refractors. But people that want to do deep sky observing use reflectors, and you just deal with the diffraction problems of the reflector. So you have your two basic types. You have reflecting telescopes and refracting telescopes. But there's lots of ways you can actually do reflecting telescopes. The first one is called prime focus. So you have a big telescope, and you put your detector exactly where the light gets focused. And that means you put a cage there, you put your detector there, and you swing the whole thing around. But you better have a really solid tube for the telescope, because you're going to have, or some sort of structure for the telescope, because you're going to put your detector right at the prime focus. And sometimes in some telescopes you might find even a cage where people would sit inside the prime focal chamber and ride the telescope for the evening. That makes for an interesting evening. And there's, of course, the Newtonian focus, which was developed by Sir Isaac Newton, which is a little secondary mirror popped out to the side. And another one is called the Cassegrain focus, where you're going to be blocking the light anyway, so why not just cut a hole in the mirror, make a circular hole in the mirror directly behind the secondary mirror. Now the secondary mirror, then, you make it have a little bit of a curve to it so that extends the focal length of it, so it makes a larger image or a better plate scale. So the Cassegrain mirror allows you to put a detector right behind the mirror, which is a good place in terms of weight. It's a fantastic place in terms of weight. It allows you to balance a telescope and make a really stubby telescope into a longer telescope. A third thing that you'll find, which is much more common at research grade telescopes, is called a Naismith-Coudet focus. And there's a secondary mirror and then a tertiary mirror behind the secondary that sends it out along the axis of the telescope's mount. So the telescope will be mounted in a fork or something, and inside the fork mount is the perfect balance point. And then you make a hole in the fork, and you send your light out that hole, which is in the balance point of the yoke of the telescope that's holding it all up. And that's called a Naismith or Coudet focus. So that particular kind of focus is incredibly useful, because now you don't have the instrument riding the back of the mirror. It's off to the side. It can be set up on some sort of platform off to the side, and you just rotate the telescope and rotate the thing, and it just stays put. So this is the best way, because now the telescope only has to do pointing, and that's all it cares about. You don't have all this extra weight. And that's the Naismith-Coudet focus is a very common thing for major research telescopes. So next time, I'll show you some of those major research telescopes. I've only been to one in that area and a couple of others, and I've helped work on one way a long time ago. But we'll look at the different kinds of major astronomical observatories next time. See you soon. A very long time ago, when I was a little boy, we still had film and film photography, which meant there was a piece of film, a negative on which you would take your image. You'd focus the camera and you load that film in there, pull the film across the reel, and hope that no stray light got in there and didn't get too warm and all sorts of stupid stuff. And if you did it right, and you took the film out of the canister and submitted it to the Kodak company by mail, they would mail you back in a week or two, all of your pictures. And that was with a standard 35 millimeter or those little 110 things, those little clicking points. Nowadays, it's a little easier because people take snapshots with digital imagery, and digital imagery comes about with the revolution of this thing called the charged coupled device. CCDs are basically light buckets that can accumulate charge on the surface of a grid. And the surface of the grid and the buckets in which they accumulate the light, what they do is they're photosensitive to specific colors and specific wavelength bands, and then when you actually reconstruct the image, you get an image that you see. Well, so what we have here in this first slide, and what you've been seeing me talk over, is actually what the camera looks like. And so you have a bunch of pins that go into a charge coupled device, and actually the CCD itself is the gray material in the center. And you'll see a bunch of leads going out from the gray material, and those things actually draw the image out. So let's see exactly what we're looking at. If we then take a strong zoom in on just one corner, what we're looking at here in this section is basically one of the pictures for a detector on, say, the Hubble Space Telescope or other detectors. But the important point is such astronomical detectors. If we zoom in very tightly, you can see the grid pattern on this letter A image that we see, and they're very, very, very tiny grids. So the light drops upon the grid, and it excites an electron out of an atom, and that electron is a current, and so it gets stored in a voltage, and by a voltage and below the collector area. And then that gets read out periodically. Maybe you wish to take a 60-second image, or maybe you want to take a 1-second image. You expose the CCD with a charge across it, and then that'll accumulate a series of basically a one-to-one, almost one-to-one, of the total number of photons that hits the charge coupled device. Those things then accumulate the total number of electrons that are freed by the photons coming into the detector. And then you read, essentially, the total number of electrons that get freed by the photons. And you see on the top of the image of letter A, you see what kind of looks like a gated readout image. And early charge coupled devices said, okay, everything's all read in. You change the voltage across it in a periodic way. Read it from one row at a time by pulling the charge by voltage differences into the read array, and then you dump them out once you've read how many charges are in each bucket. And you do that for every single row, and each row moves up into the read array at the top. And eventually you read out exactly what you have. So let's go on and look at what we mean by this readout array. We can see that many of these slides come from Pearson Education, just so you know, and come out of Macmillan Pearson Education textbooks. So I'm just using what they use. You can find these all over the web, no matter what, and they're pretty much everywhere. But what we see is that there's the buckets that look like a grid in the lower portion of it, and yes, they're very small. They can be tenths of millimeters in size, and that's actually a pretty big array. These are kind of like the arrays that you might see back when things were really beginning, say back in the 1990s or so. But they're not indicative of today's extraordinarily high resolution arrays that you might find in an iPhone 10 or in a Droid. So you can see that the bottom half of this image are a series of grids, and those would be where the buckets are, and then across are the two readout arrays that show you the voltage difference in a given array. So the entire row would be moved up into the read array, and then the total amount of electrons in that read array would be pulled into the final read array to see exactly how many, what the total charge that was accumulated in that bucket. So that's how we do it. So what happens is then you build row by row by row a series of things that says how many electrons were in each row, and you read them row by row by row, and you find that you build up an image by saying, oh, in this one there were 0, in this one there were 1 electron, this one had 3 electrons, this one had 7 electrons, maybe this one had back down to 1, and then this one had maybe 7, 9, or whatever. And the total number of photons that were incident upon the detector is almost 1-to-1, or pretty close to 1-to-1. It's a very efficient array. These very efficient arrays will say maybe 70% efficiency. So let's call it 70%. So if you see on this particular image, you see number 9. So that was maybe there were 16 photons that, or maybe more like about 14 photons that fell on it, and it detected 9 of them. The others were lost. They didn't impact and free an electron from an atom such that it could be captured in the array below. But then when you read them out, you get an image. So black would be 0 and 9 would be white. So the more photons you have, the brighter the image. And so you get this pixelated sort of appearance. And in the very, very, very finest images, no matter how small your images are, eventually a digital image will look like this at some layer. Even the best digital imagery will eventually look like this at some point, where you simply say, this is the pixel, this is its brightness at this value. And notice this is a black and white sort of image, so you have grayscale that goes from black to white, and the grayscale is adjusted for that. So we can have different gradations of it. So if you think of like a 256 color scheme, maybe we just have, that's a different deal, but let's say we're just saying how many, there's 256 shades of gray. So we could say, we could in theory say that we could only tell the difference between 0 and 256 electrons. That it's kind of shallow, but perhaps the readout array is better than that. Maybe you can get thousands, but then if the display is so poor that you can only read 256, then there you go. In any event, so here's how a more modern CCD schematic works, is that the image capture area is on the top, and the actual size and arrangement of a CCD doesn't have to be square, it can be rectangular. They tend to be square-ish, but if you can capture the entire, but some of them are rectangular. They will say the image capture area is where the light is incident upon, and what will happen then is the storage area, all that image gets dumped across by voltage differences into the storage area, and then you do you then serially shift them out of the storage area, and then do a amplifier to multiply it, because individual electrons, that's a really small output. So the output amplifier actually amplifies multiplies the total number of electrons in there. So if you have one electron, it'll dump like, maybe multiply by 1,000 volts, so you can actually read the image. So you catch it in the image capture area, it gets dumped over to the storage area 1 to 1, and then you shift from and then you go one at a time into the shift register, and then that gets dumped into the multiplier, and then out to actually see exactly how many electrons there were. So by that way, we can then process the images in order to maximize the data aspect of it. So really in astronomy, we don't really care about color images per se. We're more interested in the total number of photons that fall in a given location through a filter. So we'll always put some sort of filter in front of the detector, and we'll say, well, this is a red filter, or a blue filter, an ultraviolet filter, or a Johnson U, or a Johnson B, or a Sloan little u, or a Sloan little v, any number of different kinds of filters. And as the light passes through that filter, everything else except the light that can pass through the filter is then incident upon the detector. And that shows us the location of where it happens and how bright it is at that location through that filter. So we can see that all of these objects, they might be, say, visible light objects, and as we have low resolution on the left, and it gets higher and higher resolution on the right. And the resolution is dependent on how many pixels there are in the CCD, as well as the aperture of the telescope and the surface area of the telescope and the resolution of the telescope. So we can see that at a low resolution, we've got big pixels, and as we get better and better resolution, we have fewer and fewer pixels. So in general, what we always look at with telescopic imaging is that telescopic imaging is all about the readout of an array into an array of pixels. So where did this really come from? This comes from an idea of what's called the photoelectric effect, and the photoelectric effect basically says when you have a photon, which is a particle of light, incident upon an atom, if it has the right amount of energy, it can liberate that electron from that atom, and then the electron can then be stored in a voltage trap until you can read it out. So the efficiency of CCDs can be upwards of 70 to 80%. Old photography was efficient only about 1 to 2%. So the old photographs that you might see, that's why they took so long to make those photographs. And if you look at photographs from like the 1880s and 1890s, you'd see that their eyes are blurry. That's because people couldn't keep their eyes still. And so the reflected light off of people's eyes usually looked blurry because you couldn't hold still. So you could stand still, but your eyes would move. And so if you look at the old pictures, it took so long to make the image that it weren't clear on the eyes. That's kind of an interesting thing about old pictures. So now the readout is so incredibly fast that you can take millisecond images or some with certain CCDs even faster images than that. But in general, your phone works, your iPhone and any other detectors that are like that work in a very similar way, in that all the light gets trapped in these boxes, and then the boxes get read out one at a time, box by box by box, and however much light goes in there gives you the brightness at that location through the filter. All right, so next time we'll be talking more about light and telescopes, and to see more about exactly how you turn this kind of image, or an image that's created by a CCD, into a color image, go look at my M20 reduction by using GIMP and FITS Liberator, which is also on my YouTube channel. Today we're going to be talking about some very famous telescopes and how they contribute to astronomy. But mostly we're just going to get you familiar with some of the great telescopes. I'll show you some of their websites and what to do to look for. And of course we're going to start with the Hubble Space Telescope, arguably one of the most important telescopes ever to be created in the history of mankind. It's orbiting at about 300 miles above Earth in a continuous orbit, going around the Earth every 90 minutes or so. And it is one of the most important pride and joy jewels of global science, and its impact on humanity cannot be underestimated. It's one of the most important tools, and if you were going to look back in 200 years from today, probably one of the most significant technological things that's ever been built is the Hubble Space Telescope. So we're just going to give some basic details on it. Yes, it's a big telescope, and they're the websites to go look at. The HubbleSite.org, which is run by a consortium with the Space Telescope Science Institute, as well as the European Space Agency's version, which is www.spacetoLescope.org. And this picture you're seeing was taken by people on a servicing mission as they approached the Hubble Space Telescope or left it in order to just show it over the great deserts of Africa. All right, so the Hubble Space Telescope here is being shown to be either captured or released. I believe it's being released by the space shuttle orbiters. And what they do is they just saddle right up to it in orbit, and the arm would go out and grab it. Basically, you're just going to, as this Hubble Space Telescope orbits the Earth, the space shuttle did 5 different servicing missions, one launch, and then 5 missions to service the Hubble Space Telescope. And so all you do in order to service it is simply fly just as fast as it does, or orbit exactly next to it, and then go right up to it really slowly and latch on, and then you're together. Both of these machines are extraordinarily massive, so your relative speeds have to be very slow, or else you'll twist and torque and nothing will ever happen, because momentum still works even though you're flying really fast and seem to be motionless with respect to each other. All right, so some basics about the Hubble Space Telescope. It's basically a Cassegrain, an elementary Cassegrain type design. There's a big 2.5, roughly 2.4 meter mirror. That's the primary mirror, and that reflects onto the secondary mirror, which then goes back down through the hole in the back of the primary mirror. And all the instruments lie behind the primary mirror. So the Hubble Space Telescope has a big cover for it, and that cover just closes if there's problems, or if you just want to end on flight. And the solar panels provide all the power to it. So there's a number of guidance sensors and a number of guidance small telescopes that track it and keep it aligned as it's moving around, and gyroscopes keep it aligned as well. So all of the instruments inside of it. There's numerous detectors inside of it that can pick off the light as it's coming through. So it's about so let's go look at the actual the Space Telescope itself. So if we go to Hubble site, which is www.hubblesite.org, which is run by NASA, you can look and see all sorts of interesting things when it was launched in 1990, the servicing missions, learn more about it, where it's orbiting in space. You can look at the various pictures of the mirrors, its history, all about how it's built, what pieces of the spacecraft exist. So I would suggest go take a look, because Hubble site has also some of the most amazing images that you'll ever see. And these images are pictures that are taken by the telescope and then constructed by a post facto, and because they all come out black and white through filters. So it's not like it takes a color picture. It again takes a series of filtered images, and all the color images are combined together. So you can go and just take a look at your favorite picture, and just for fun and enjoyment, let's go take a look at, say, this one, which is of a galaxy, NGC 1015. The release date was February of 2018, and we can see a nice, beautiful image coming from it. It's just absolutely gorgeous, and the imagery that you can see coming off it is astonishing. The detail of the Hubble Space Telescope cannot be underestimated, and let me show you exactly what that means. So first, we'll go back and say there's also really some cool videos that tell you some things about the Hubble Space Telescope, and also things that have been observed with it. There's also some amazing stuff about some things that were good friend of mine, Frank Summers at Space Telescope Science Institute, did some fly-throughs, and fly-throughs meaning taking images taken by the Hubble Space Telescope and rendered them in 3D. And so let's go take a look at some of the more interesting aspects of what we mean by the benefit of Hubble Space Telescope. Well, it's in orbit. And because it's in orbit, it doesn't suffer from all of the effects of the atmosphere. And that was the main drive for getting this telescope up in space to begin with. So let's actually go back to the beginning. I'm going to kick out of this a little bit. Boom, boom. So there it is. It's up in orbit above the Earth's atmosphere, which dims the light and causes atmospheric seeing because clouds get in the way, rain gets in the way, and that just doesn't happen with Hubble. So it's an incredibly valuable piece of machinery. So how does it get the information down? Well, when the Hubble Space Telescope takes the image, it doesn't directly broadcast it. It sends the data by radio over to, say, some tracking and data relay satellites. And then those satellites store the data and then send them down to ground stations at various locations, specifically at White Sands Missile Range down outside of New Mexico. And then that data is then transferred over by wire over to the Goddard Space Flight Center in Greenbelt in Maryland. And right over there next to Goddard is the Space Telescope Science Institute in Baltimore, where all of the computing facilities for it live and where the data is stored. And the neat thing about the Hubble Space Telescope is that all the data that you see is available to you, and you can actually go download it at the Hubble Legacy Archive website. So you can go play with the data, because that's one of the reasons for it is that after researchers have done their duty with it, that gets put up on the website. All right, so let's see what we have. What's so important about this? All right, so the resolution is the key. The clarity of the resolution is amazing. So on the left-hand side of this image is from the Palomar Sky Survey. The Palomar Sky Survey was done in the early part of the 20th century, as in the 40s and 50s, and the goal of this was to take a photographic survey of the sky. And the image on the left is about a 1 degree by 1 degree image in the red. I believe this is a red image of specifically NGC 403839, a pair of interacting galaxies called the antennae. And so we can see that there's a bunch of stars in there, and there's this fuzzy sort of antennae thing. And at long, deep exposures, such as taken by the Palomar Observatory, it's a really pretty image. And you go, wow, what is that thing? So I want to see that really close up. So let's see what we can do with the Hubble Space Telescope. On the right-hand side is the core area, the two interacting cores of the antennae taken by Hubble. And so let's go zoom in a bit. Now, when the black and white image on the left, that's a 60 by 60 arc minute or 1 degree image. So 1 degree on a side, which is approximately the same as your thumbnail held at arm's length. So that the antennae in the sky, if you could see them, because they're pretty dim and extraordinarily faint, would be about the same size as one of the large mare in the moon. All right, so if we zoom in and only look at the inner 5 by 5 arc minutes, or 60 over 5 is about 1/12 of a degree. So that's a very, very tiny amount. So 1/12 of a degree, or 5 by 5 arc minutes. We can see that the photographic survey doesn't have a lot of resolution. We can't see really fine features. We can see there's some bright specks on the left. There's some fuzziness as a result of the photographic image, but it's really unclear. And that kind of fly sort of thing was just a piece of dust on the photograph as it was taken. And so that's all there is to it. You got this piece of dust on there. And the same image, 5 degrees by, well, actually a little tighter than that, is on the right by the Hubble Space Telescope. So we can see that the photographic survey, which was done on the ground under pristine conditions, when there wasn't much light pollution, and had all the time that you needed to take in order to take these amazing images on the ground. We see on the right-hand side the details that the Hubble Space Telescope is able to pick out. And so looking really carefully, you see the bright spots are resolved into other things. So let's zoom out even further and go even to the inner 2 by 2 arc minutes. So the square on the upper right is 2 by 2 arc minutes, which is about the same size as a small crater on the moon, or at least a relatively large crater on the moon, because the moon is about a half a degree, or 30 arc minutes across. So this would be a large crater on the moon, such as the crater Tycho, would be the size of the black and white square in the upper left. So then we look at that same dimension image. I cut it down so it's the same dimension of image on the right by the Hubble Space Telescope, and we can see all sorts of details. The details that certainly look like bright spots where it could have been some sort of active formation are certainly borne out. The colors jump out, the details jump out, and that's because of the extraordinary resolution of being above the Earth's atmosphere. We can see the dark dust lanes, we can see the pink glow of hydrogen gas, we can make out enormous star clusters, we can see the core of the galaxy and see it distinguished from the star clusters around it. And so we also even see in the fringes of the image, on the upper right and lower right of the image, we see extraordinarily distant galaxies which do not show up inside of the digital sky survey. Those distant galaxies are extraordinarily far objects, many, many, many hundreds of millions of light years away. And so the Hubble Space Telescope, with its details, allows us to see actual processes as they're going. It's not just about being able to see colors or pretty pictures. It's about being able to detail processes and notice the physics of it. Now remember, a galaxy is so incredibly large that you're not going to see anything move. However, you can actually detect, or at least posit what the flow should be in this kind of thing, and it helps you study exactly what this object, these interacting galaxies are like. So this tells us that the Hubble Space Telescope's ability to resolve objects is incredible and unparalleled. And that's its main advantage, and that's why it had 5 servicing missions. And even after the Challenger disaster, it was determined, and after the Columbia disaster, it was determined that yes, there would be a final servicing mission to the Hubble Space Telescope to keep it aloft for at least another 5 to 10 years while the James Webb Space Telescope gets ready. Well, so the Hubble Space Telescope is one of the most important space-based observatories because of its ability to get close. It's very difficult to actually put things in space. So it's much easier and much more economical to actually put observatories on the ground. And the vast majority of all science work is from observatories on the ground. And this is a series of major research observatories on the Big Island, the summit of the Big Island in Mauna Kea, Hawaii. And we see a series of telescopes, the Keck Observatory, the Subaru Telescope, NASA's Infrared Telescope, the Gemini North, the CFHT telescope, lots of little telescopes. And the reason is that on the top of this mountain, it's incredibly clear skies. You're above almost all of the clouds, above everything. It hardly ever rains there, and you can certainly see that the ground looks dry because there's no plant life at the top of the mountain. I think it's 15,000 feet. And so that's high enough that you're above all the moisture, you're above almost all the clouds, and it's a perfect location because the trade winds don't actually bring in huge numbers of storms. However, at the time of this recording, at the end of May of 2018, there's a massive volcano going off, so I'm certain that all research actions at Hawaii are currently off, just because, well, there's a volcano erupting. In any event, the observatories there benefit from high altitude because they're above most of the atmosphere and the clear and steady skies that normally abound at Mauna Kea are there. So let's take a look at a few of the telescopes at Mauna Kea. And the Keck Observatory, and the images that you're going to see here come from the Keck Observatory website, is one of the most important observatories at that top. And we can see the clouds in the distance, and they're below the observatory. So you can see that, yeah, that's a little bit of a cloudy sky, but you can definitely see that you're above most of the clouds. And you can see the two telescopes inside of the pair observatories. The original goal was to be able to do optical interferometry or binocular view, but not like binocular for 3D view, but interferometric view, so you get the effect of having a much larger observatory. So those two telescopes are identical in build, and that was the purpose of them, but it's extremely expensive and time-consuming in order to run it that way, so it's seldom done. Anyway, so let's take a look at the two telescopes. They sit at about 13,000 feet above sea level, and they're 10-meter telescopes, which means the diameter of the two telescopes is 10 meters. So let's take a look back there again. And so we see that these domes are about 30 meters or over 100 feet, more like 125 feet across. And you can see there's little cars in the background, and those cars show you dimension and scale, because big truck couldn't even fit a big truck across the mirrors. So the mirrors are actually segmented. They're not solid mirrors. Well, the segments are solid, but it's not one big mirror. Making them in these honeycomb patterns actually does the trick for it. So the light shines off the mirror, the main primary mirror, which is in segments, that goes to a secondary, and then that goes to a tertiary mirror, which then shoves it out to the side to what's called a Coude focus or a Naismith focus, and that allows and you can put you don't have to have the instruments for imaging or for doing spectroscopy on the telescope. You simply bounce it around a whole bunch of other mirrors and then send it down into a room where the data is going. So this is what the telescope looks like close up. Again, this image is from the Keck Observatory website itself, and we can see that the mirror in the center is the 36 segments, and we see the tertiary mirror, which has some baffles around it, and the hole to the side goes off to the Coude focus, which then goes down into the data area. And it's held aloft and the secondary mirror is held aloft by a spindly, rigid structure, so that the secondary mirror simply does not move no matter what the orientation of the telescope is. And there's another view of the observatory where we can see the secondary mirror in reflection. So you see all the hexagonal shapes. Those are the primary mirror segments. We see the tertiary mirror inside the black baffle in the middle, and then we see a hexagonal sort of thing that's kind of off-center, and it's to the right of the frame, which contains the secondary mirror. All right, so then that particular observatory has done amazing studies. One of the more important studies that it's done has been used for us to look at the center of the galaxy, and I'll show you that in a bit. Another important telescope for observing is the Gemini North. Now, Gemini North is the north version of the telescope. There's another identical telescope to it in the southern hemisphere, Gemini South, that's in Chile. And these two telescopes are the exact same, the same specs. And what's neat about this is that you can get an interferometric view
across from two things across from a quarter of the diameter of the Earth. And that was the plan for it. And so if you have something, you can then have a very large baseline array and see if there's any kind of views from that. So the Gemini Observatory on the right-hand side, which is the silvered dome, the larger silvered dome, that's the one that has an enormous telescope in it. And here's the view of the Gemini North. And this comes from the Gemini group. It's a very large telescope as well. It's not as large as Keck. And then if we zoom down to a place that I know very well, which is in southern Arizona, if we go down to Tucson, Arizona, which we see in the distance there, we can go to Kitt Peak Observatory. And Kitt Peak National Observatory is in southern Arizona. We can see the clear skies overhead and a starry sky. And I have friends who go and observe there on the 2-meter class mirror that's at the top there. There's also a solar observatory there. Lots of little telescopes. It's a beautiful place to go observing. And a good friend of mine goes and uses that telescope all the time for his studies of star clusters and planets. So Kitt Peak National Observatory is someplace you can actually go and visit and go on tours. And in fact, some of the smaller telescopes, you can actually book time on them as an amateur if you wish. And this comes from the National Optical Astronomical Observatory website, or NOAO website, and that's the administration of the Kitt Peak National Observatory. Now, if we then go to another facility owned by NOAO, which is the Cerro Tololo International Observatory, NOAO is one of the groups that's involved in administering this, and Cerro Tololo is down in Chile, in an extraordinarily high altitude in the southern hemisphere, at I think it's about 14,000 feet. And these telescopes, they're incredibly important for observing southern hemisphere objects. But Chile and the Chilean desert just doesn't get any rain at all. It hasn't got it for thousands of years, and it's perfectly situated way up high in the mountains. And the Chilean government has bent over backwards to try to help these observatories out into the southern hemisphere. And it's a pride. It's one of the elements of great pride of the Chilean observatory. And kids in schools go on up and visit these things occasionally, and they consider astronomy one of the key things that gets taught in grade school. So that's Cerro Tololo, which is partly administered by the National Optical Astronomical Observatory in the United States. Now we can go to the European Southern Observatory, and ESO is run by the European, it's a consortium of universities and institutions that is called the European Southern Observatory. And they've got a number of amazing facilities, and one of the more amazing ones is the VLT, or the Very Large Telescope in Atacama, the Atacama Desert in Chile. And you can see from this helicopter drone view that it's really out in the middle of nowhere. The Atacama Desert really has nothing going on. There's literally nothing out there. It's just, there's almost no plant life to speak of. I think the only plant life is inside the rocks themselves. And so the VLT has amazing views of the night sky, and especially of the center of the Milky Way. And these pictures, of course, are credited to the European Southern Observatory. And we can see that the dark skies, even with this camera view, which is just a wide-angle lens using a telephoto, just a DSLR camera, can show amazing views. And we see above to the left of the observatory, that's the belt of Orion and Barnard's Loop going around it. And we can see the band of the Milky Way in the sky quite prominently. And so these observatories have an unparalleled view, and the 4 telescopes can all be pointed in the same direction or used independently. And there's another view of it from the distance. And there's one of the telescopes inside its frame. These are massive scopes, and they're like huge toys to be played with, if you wish to consider it that way. These telescopes, you have to really be careful, because you don't want any water dripping inside these things, so they can only be opened if there's no moisture at all inside there. And you can see they have all sorts of baffles to try to get rid of moisture and keep the damp and get rid of dust and keep airflow going through that, so the air temperature inside the dome exactly equals the air temperature and humidity outside the dome. That's critical because you can get a microclimate inside these domes. The domes are there for protection, but really they hinder a lot of things, because if you can have different air quality inside the dome and outside, even though the hole is wide open. And that can affect the viewing of the telescope. All right, so the VLT is an incredibly large series of telescopes, and we'll go down and check out their website in a little bit to look at the specs, but you can see they're massive scopes that are on the order of many meters in diameter. So what's the reason for all this stuff? What do we do? High resolution astronomy, what the goal is, if you put a telescope on a mountaintop or deserts, you get above all the atmosphere, you get away from moisture, which causes clouds, and that breaks up seeing. Because if you go out on a cloudy night or even a humid night, it looks kind of foggy and the stars aren't very good. So if you want to, and that makes bad seeing. So no matter what you do, even if you put a telescope on a mountain or up in the deepest desert on top of the tallest mountain, you'll want to put them in space. Or if you put them in space, the thing is that you can actually mirror, or at least use specific kinds of optics in order to approximate what you get in space. So remember we talked last time about the nature of seeing. We have a diffraction limited seeing, and if you're in space you can get that. But on the ground, you can't because of seeing, because of the distortion due to the atmosphere. So what do? Use adaptive optics. And this, again, is from European and Southern Observatory, and Yuri Beletsky took this wonderful image of a laser guide that's being shot at the center of the Milky Way in order to take pictures of or try to image the center of the Milky Way in infrared. But that laser actually serves an incredibly important purpose. It's not like it's shooting at the black hole in the center of the Milky Way. Its goal is to create a fake star in the sky. And that fake star, we know where it is, and it's going about 60 or so, it goes about 20 or so miles up, and gets to the top of the atmosphere, reflects off the molecules in the top of the atmosphere, and it can be used as a fake guide star. And that fake guide star is an illuminated patch of sky that's just off to the side of the target that you're actually looking at. And what you do is you look at how that fake guide star flickers, and that guide star is the only effect that it has is it's the atmosphere effect. Now, you want to reduce the effect of the atmosphere because the star is coming from outside of the atmosphere, go through the atmosphere. And so the light coming from, say, this image, which would be coming from the center of the Milky Way, it has to come from the center of the Milky Way and pass through the atmosphere. And so does the laser, but the laser light goes up through the atmosphere and bounces off the Earth's atmosphere and comes back down to the telescope. And so that can be then that we can take the effect of the twinkling of the atmosphere out with special instrumentation called adaptive optics. And so adaptive optics can be used in the following way. And these things are done by the Keck Observatory group again. And there's a group at UCLA that works on the Galactic Center. That's Andrea Getz's group at UCLA. And she uses the adaptive optics, she and her group use the adaptive optics to try to study in infrared the center of the Milky Way. Without adaptive optics, meaning without accounting for or using some tool that like a laser guide star that flickers, that you know exactly how it flickers because you observe it, and to remove that effect, you get the blurry image on the left. And it's a pretty darn good image of the center of the Milky Way without adaptive optics. But when you turn on the adaptive optics, you get the thing at the right. Notice the diffraction of the bright star in the upper right on the adaptive optics group. It has a hexagonal shape. That's because the mirror of the Keck Observatory is a hexagonal shape. Those hexagonal shapes then become the diffraction pattern of the stars in the sky. And Sagittarius A star is the thing that's being pointed to in the center, and that actually is not, there's not a little bright, it seems to be a little bright point, but that's actually the center of the Milky Way, and somewhere right where that arrow is, there's the dynamic center of all those stars in the sky that we see in this image. And the dynamic center, especially the faint ones, because they're so distant, those faint stars, they're faint because of their distance, are orbiting something that's truly massive, and that we can actually study the motions of these stars, and that's what Andrea Getz's group has done at UCLA, and it's an amazing, amazing thing they're able to do. All right, so this is the sum of one of the things they did, and you can compare and contrast between with the adaptive optics on and with it off. And the little plus that's in the center, that's the location of the center of the Milky Way. And again, this is from the UCLA Galactic Center group, which I'll show you their website in a bit. All right, so how does adaptive optics work? So let's actually take a look, shall we? Hopefully the little video is running, and this is courtesy of the Gemini Observatory because they're the ones who created this little video. So we'll take the Gemini Observatory. The light bounces off the primary mirror, goes off to the secondary mirror, goes down through the hole in the primary mirror, and it doesn't go directly into the instrumentation. It does the following thing. Now you got to have a computer hook up to the thing. It goes down through, reflects off a secondary mirror, bounces off a few things, and finally gets to a detector. Now, before it gets to the red path, we want to actually distort the view of the picture. So it comes in these kind of waggly pancakes, and the waggly pancakes have the distortion due to the atmosphere. But if you then have a feedback loop, you can actually use the feedback loop to distort the little tiny mirror and get rid of effects of the seeing. So let's go back and take a look at that again real quick. So I'm going to try to pause it, and then there's the little tiny square feedbacky things. You can see the incoming pancakes are all wiggly, and then we use adaptive optics to shape the mirror coming out. And we see that in the first reflection reflects it off of a half silvered mirror, so we lose some of the light to go to a detector that then quickly goes back and reshapes the mirror that it's reflecting off of to accommodate the shape of the light that has been how it's been distorted by the Earth's atmosphere. And so this can be done if you have a star of known brightness in the field, and that star can be a guide star, a laser guide star. So that's what's done. So you have the adaptive optics then distorts this tiny mirror just a little bit in order to show that tiny mirror on the side gets those little bitty pistons inside the mirror shape it just by fractions of a millimeter. These aren't big changes, but they're just enough, and they have to be done extraordinarily rapidly in order to accommodate the twinkling of the Earth's atmosphere. So the mirror can be deformed slightly by these little tiny things, and then it clears up the image amazingly. And that's the goal of adaptive optics, is to actually clear up the image. And Gemini Observatory is run by the National Science Foundation as well as the Aura Consortium. High-resolution astronomy. The goal is we use either really big telescopes, get them up on top of mountains, or get them into space so that we can do amazing resolution, such as we've seen with the Hubble Space Telescope. And that is the goal of high-resolution astronomy, is to be able to see extraordinarily detailed images such as these of the antennae. All right, so where can you go to actually look at these things? Observatory.org, which shows you all of these things and talks about the nature of the telescopes. You can see the observatories themselves, pictures that have been taken using them, as well as pictures of the observatory, as well as current research and news that's happening at the Keck Observatory. Some amazing things happen here. Of course, since it's May 17th, the observatory is, of course, having its difficulties as a result. And that's what's been going on there. Astronomy gets talked about up there and at all sorts of locations, and we have nice news coming out of there. But if you just go to the news and videos, let's go look at science news or events and photos of the location. We can zoom down through and take a peek at some of the fun stuff that they're looking at. So, like the roadmap for planet hunting, Keck Observatory has been used to actually verify planets around other stars. So that NOAO, which is noao.edu, has a series of things. There's a visitor center at Kitt Peak National Observatory, which you really should go see if you get a chance. The Large Synoptic Survey Telescope is about to be built. It's under construction, and that's going to be down in Chile as well. There's the Cerro Tololo Observatory, which NOAO is part of, and Kitt Peak National Observatory down in Tucson. So Kitt Peak is someplace you really should go visit if you ever get a chance to go into a dark sky. CTIO has a 4-meter scope, a 1.5-meter scope, and another meter size scope down in Chile. They have lots of things for education and public outreach. So if you want to learn things about them, they have beautiful image galleries, and I invite you to go take a look, because the images that you find here appear in prominent places, such as Astronomy Picture of the Day, and sometimes they even appear in national news media. So if we go look at galaxies, we have all sorts of cool thumbnails of pictures that were taken there. Say M33, the Triangulum galaxy, and so NOAO is a national treasure, and you should go take a look at their website. The next one is the European Southern Observatory, and they have a number of instruments and telescopes. The Paranal Observatory, which is the VLT, the 4 8-meter telescopes. They can be used individually or used as a large collection. They also have an observatory at La Silla, which is a 3.5-meter scope. The Apex Atacama Pathfinder exhibit, which is Apex. But one of the more interesting ones is the ALMA array, which is a sub-millimeter array, which is light that is in the microwave wavelengths, and that has to be at extraordinarily high altitude in order to actually look at them. So each of these 12-meter radio telescopes are out in high deserts, and they put themselves together to make amazing images. And the goal with the ALMA array is, let's just take a look at that real quick, because we're going to eventually get to it. See, the ALMA array has a number of amazing things that go with it. Most notably, it has the ability to see the science that it gets is with the cooled universe, molecular gas and dust, and looking at the formation of there's the antennae again. So let's take a look. The antennae through the ALMA array. And so we see the Hubble Space Telescope and the Hubble image in the background, but we see, if we look closely, we see the ALMA array, which shows the cooled gas which surrounds and goes through the entire thing, the entire area. So understanding the physics can be done in multiple wavelengths. We can look in visible light, and now we can look in microwave light. And the antennae were one of the prime targets for the ALMA array when it came online. Fascinatingly enough, the European Southern Observatory is trying to build a gargantuan observatory called the Extremely Large Telescope, which would be a 50-meter scope, 39-meter primary mirror, which is just insanely large. They want to build it. In the Southern Observatory down in Atacama Desert, because it's big. The primary mirror would be enormous, and the goal would be to actually try to get the faintest objects, try to see the most faint objects around. So I would just go take a look in the images that are associated with it. One of the nice things I like about it is they have a top 100, which is a lot of fun. You can actually build an entire astronomy course on the top 100 images that were taken by the European Southern Observatory. Next, and I promise you this, which is the UCLA Galactic Center group, which is Andrew Getz's group, which has used these observatories, which has used the Keck Observatory to actually map the movement of individual stars around the center of the Milky Way, which is an amazing accomplishment. So I would really invite you to go check that out. But this is what Andrew Getz's group is known for this amazing work. And they have some amazing public outreach, their news and science, what is a black hole, what are the telescopes they use, what adaptive optics is, and some of the images and the high resolution images that they've taken. And that's where they come. That's where many of the images that I used on this video were from this website. So I wish you well, and I want you to have happy dark evenings, and hopefully you'll be able to go on outside and appreciate the sky in a different way after listening to this. And hopefully you'll get a chance to go and take a peek at all of these amazing observatories, the Keck Observatory, the European Southern Observatory, the NOAO, and how to actually go to Southern Observatory as a tourist. You can actually go there. You can have some fun by going all the way down there. Lots of fun things to do. Last time we talked about some of the big observatories around the world that are optical, as well as a couple in space. But let's actually look at another aspect of astronomy, which was developed back in the 1960s. It's radio astronomy. So let's start off with looking at the electromagnetic spectrum, which is all the possible frequencies and wavelengths that light can have, and we see that the visible portion of the electromagnetic spectrum is practically nothing. Most of the light of the universe does not come in the form of visible light. Most of the light is actually much longer wavelength and much shorter frequency. There are other wavelengths of light such as ultraviolet, X-ray, gamma rays, and infrared, but this time we're going to focus on radio wavelengths. Why do we focus on radio wavelengths? Well, if we look at the electromagnetic spectrum, we find that the Earth absorbs light at various wavelengths. Gamma rays, X-rays, and ultraviolet light are blocked. Infrared is mostly blocked and absorbed due to water and carbon dioxide. And super long wavelengths, meaning mile-long wavelength radio waves, are actually blocked by high-altitude electric charges that simply reflect them off. However, there's a range of wavelengths of radio light that just simply pass through the Earth's atmosphere uninhibited by water, carbon dioxide, anything in the atmosphere, and so can make it to the ground. So the atmosphere of the Earth is only transparent to a few wavelength regions. Almost everything else is blocked, and part of the reason we have global warming is because infrared radiation does get trapped, and all you have to do is add some more water and carbon dioxide and you trap more infrared, and that's warmth. In any event, for astronomy purposes, the visual window is what we see with our eyes, and the radio window is what we see with radio telescopes. So let's see what we mean by a radio telescope. Here's one of the more prominent radio telescopes used in the United States. It's in West Virginia, run by the National Radio Astronomy Observatory, NRAO, and this is the Green Bank facility. And Green Bank is a wonderful, steerable, 100-meter wide dish. And so that big dish just reflects radio waves up to a receiver at the top of that gantry. And so you steer the radio telescope in direction. So it's very similar to a normal telescope in that you have to point it at directions in the sky. And whatever direction you point at in the sky, that's what you get. But radio telescopes are a little different in terms of their reception and things like that. But let's leave that out for now. And we'll just talk about the nature of what it is. So radio telescopes are reflectors. Unlike a refractor possibility for optical telescopes, nobody ever makes a radio refracting telescope. That wouldn't make any sense because the wavelengths of light do not get affected by it as they go through glass the way that a visual light does. So we build reflecting type telescopes, and the surface of the reflecting type telescope just simply has to not absorb radio wavelengths. So you can use aluminum, typically. It makes it lightweight structure so that you can actually put these things in large areas. And this valley in Green Bank, West Virginia, is a national radio quiet zone, meaning when you want to go there, you can't take a cell phone. And in fact, you have to use diesel engines because most modern cars have computing systems on board, as well as the fact that modern vehicles actually emit huge amounts of radio light. So there's all sorts of restrictions about what kind of vehicles and what kind of radio anything you can install in this area around this observatory. So it's a fascinating place to go if you want to completely get away from your cell phone. All right, so radio telescopes are similar to optical telescopes. They have a prime focus setup, meaning the light gets reflected and it's received at the prime focus. Because the wavelengths are longer of radio telescopes, you don't have to worry so much about the imperfections on the surface of the scope itself, because typically the wavelengths are longer than the imperfections on the telescope. So let's say some bird comes along and drops a load inside of the radio telescope. Well, that's on the order of a centimeter or so in terms of size, and the wavelengths of light can be millimeters to meter light wavelength. And so basically, and also the large surface area means you're going to not worry about that particular little thing. Of course, you're going to clean it up, but that's not really of a big deal. So radio telescopes must be made large because longer wavelength means poor resolution. All right. So the typical focus is it bounces it off, use a parabolic reflector, it collects it up into a focal point, and the parabolic reflector goes to the prime focus, and then, hey, when you get to the prime focus, then you can put your detector at the end of the gantry too. All right. The second largest, well, for a long time it was the largest radio telescope in the world, the 305-meter dish at Arecibo down in Puerto Rico. This is an enormous dish made in basically out of a hillside, out of a mountain area, and so it was a natural depression in a mountain. And basically, it was put there. The dish can't be steered, unlike the one in Green Bank. But what can be done is you can put the detector at different locations, and that allows you to look at mostly things towards the zenith or straight overhead. But you can get some off-axis things with work. But basically the collecting area is an enormous dish, and that enormous dish at 300 meters, it gets kind of dirty, but that's not a big deal because what's being reflected is radio waves. So they're long wavelengths, so you just kind of go and occasionally have some people go clean it out. As a result of the massive hurricane that came through Puerto Rico, one of the few places that could actually be used as a staging area to help the people of Puerto Rico was Arecibo, because it had its own independent power supply and its own independent water supply. So Arecibo was one of the observatory itself and the science facilities were used as staging areas to help the rest of the country in recovery. So sometimes radio telescopes and astronomy can do actual direct benefits to people, and that's the nature, and it's what's really beautiful about it. And people in Puerto Rico do love their Arecibo Observatory because the jobs that it provides, as well as the interesting science that can be done there, and it's perfectly positioned in order to look at the center of the Milky Way too. Anyway, so there it is. It's a big thing. However, it got dethroned in 2016 by the FAST Observatory, the 500-meter aperture spherical telescope observatory in China. It's 500 meters in diameter. It's not strictly speaking spherical, and because of the design of how the telescope works, it only can view using an illuminated area of 300 meters. So sure, it's 500 meters in diameter, but they'll never actually use the entire 500 meters at once because of the way the receivers are set up. But it was a major accomplishment to build such a massive thing, and it's in operations as of the fall of 2016. One hopes that the United States can continue to fund the Arecibo Observatory, which is managed by the National Science Foundation, and the Arecibo can then become and still maintains its great position in radio astronomy in the world today. Well, it's not just about big dishes, and it's important to have big dishes, but radio telescopes you can do other things with them. Radio astronomy itself, because of why do we make these huge dishes, first of all? Well, the longer wavelength means it's got poor angular resolution. Remember, the longer the wavelength, you have that equation that shows that the resolution is dependent upon what angles you can resolve depends upon the wavelength. And if it's long wavelength, that means you have poorer angular resolution, or you can only resolve large angle things. However, one great thing about radio astronomy is you don't have to worry about clouds or rain. You can even have snow on the thing and it doesn't work. It doesn't interfere. So whereas optical observers must wait for perfect evenings on cloudless, dark skies at high elevation, now you can put up a radio observatory anywhere so long as you've got enough surface area in order to mount the thing up. That's why people have radio dishes on their roofs. Well, mostly for television and FM and AM broadcast, but it's still the same principle. Anyway, you can take observations all the time, and because their wavelengths are different, you get completely different information about the objects you're looking at. And here, we're looking at Centaurus A. That previous image was of Centaurus A, so let's look at a more recent version. And this was assembled by the Goddard Space Flight Center Visualization Group, these two images. But the optical image on the left was taken by the Capella Observatory, and the radio observation was done by Fane, Cornwell, Eckers, Morgantani, and Junks. And what they did is they made a more recent map of the Centaurus A active radio galaxy using the radio wavelengths. So on the left-hand side, we see the only optical observing, and on the right-hand side, in orange, is the radio emission. Notice they're completely different. So we get totally different information about physical processes that occur by objects when you look in radio wavelengths as opposed to optical wavelengths. Completely different processes occur. On the right-hand side image, the radio is overlaid on top of the optical image. It'd be very hard to distinguish it because none of the stars that are in the field, which are all foreground in our Milky Way, would ever actually show up in these radio observations. They'd be very faint sources. But this one radio galaxy, which is about 12 million light years away, is an incredibly bright radio source in the sky. And the angular size of it is about half a degree in the sky. Anyway, we can do other things with radio that we cannot do, or what just as easily with optical, is to do what's called interferometry. Interferometry, instead of building, say, a 300-meter scope or a 500-meter scope, what you do instead is you build a large number of smaller telescopes. And you take the information gathered by all those smaller telescopes and use computing facilities in order to deduce what they are, and then make an effectively large telescope. So it's as though this is the Very Large Array displayed in the upper left image. And the Very Large Array is in Socorro, New Mexico, in the desert in the deserts of New Mexico, and it can be the dishes can be both in this tight formation and spread out. You can see the road leads to how far apart they can go. So when they're in a maximally spread out position, the entire telescope, the effective telescope, is the size of the separation between the dishes. So all you have to do is take data from all of them and use computing facilities to recombine them together. And that's what the people at the VLA at NRAO do, is that every now and then they say, okay, well, this particular study, we need the dishes, we need a tight collecting area, we don't need this large, we need a small beam, tight collecting area. So they bring the dishes into a smaller formation. But if you want to have a high angular resolution, what you do is you spread the dishes really far apart. And then you get less, you have an effectively larger surface area or effectively larger aperture, which means that you can get greater resolution. So by moving the dishes around and combining them together, you can use interferometry to make many little telescopes act as one. And there's another image of the Very Large Array in Socorro, New Mexico. And they occasionally hold symposia there. And when I was in grad school in New Mexico State, we occasionally went up just to say hello and also go to symposia at the visitor center there as well. And it's run by the National Radio Astronomy Observatory, or NRAO. And we've featured, and there's some of the dishes, as we've seen. This is a relatively older photograph, but you can see that they're very large dishes. Each of them is extremely big. What can you do with these things? Well, again, you can look at different wavelengths of light, and the VLA can look in millimeter-style wavelengths up to centimeter wavelengths of light. And as combining them together, when you do combine them together, you can get objects such that you see in this image. In the central main image of M87, which is another active galaxy, we can see in nearly 1 meter long wavelengths, or 90 centimeter wavelengths, we see a huge, like, puffy structures, which is yellow, but in the center it's very bright. So it's actually too bright for the image, or it just washed it out. But if we look in 20 centimeter radiation, we see that there's a small jet-like structure. And if we look at 2 centimeter radiation, which is shorter wavelength and therefore higher resolution, we see definitive jet-like structures. And 7 millimeter wavelengths, we can see some objects that seem to be moving. So each one of these images shows smaller, higher and higher resolution, going from longer wavelength, which is poorer resolution, to shorter wavelengths, which is better resolution. And so you can get fascinating structures which you simply do not see in optical wavelengths. In optical wavelengths in M87, we do see the jet, but we don't see everything else associated with it. So what is creating all of this jet-like structure, and what is involved in it? And first we study the radio emission and go and discover these things. So really, when we opened up the radio observatory in the 1960s by actually pointing radio telescopes at the sky, we learned a lot more about the nature of the universe. And that's a key thing. Every single time we open up a new wavelength band in the sky, we learn more about the sky itself. Well, as you can see, it's been in movies too. So there's Jodie Foster with Contact. All right, so what does interferometry do? You preserve the phase relationship. So if they come in step, meaning the two let's say on the upper right-hand side, there's 2 dishes, A and B, and you can see that if they come in step, meaning the phases, the wavelengths of light, the crests arrive at the same time. Maybe a crest arrives at a crest, or a wave or a crest arrives. If they come in out of step, meaning a crest arrives at the same time as a trough, then there's destructive interference. If they come in an instep, then it's constructive interference. And so this diffraction effect that you get because of constructive and destructive interference must be taken into account, because what you want to do is look at the things that you see in the direction you're pointing the scope. But because of how radio telescopes work, you can get information from stuff that's not in the direction that you go. So it takes an enormous amount of computing time and some extremely complex mathematics in order to deconvolve the interferometry. But radio telescopes themselves have been critical in our understanding of some incredible processes around central points of the black holes in other galaxies and in our own. So it is the relationship between these waves, whether they're constructive or destructive interference, that you have to deconvolve with the mathematics and huge amounts of computing time. And so it can be a real pain, and it takes time. And you don't just like look through a radio telescope, look through an interferometer. What you have to do is you got to say, okay, let's deconvolve it. All right, so there we have that. Some more interesting things. Because of the interferometric array, we can use what's called the VLBA, or the Very Long Baseline Array, which takes a huge number of radio telescopes all over many places, and then you combine them together. They're all pointing at the same thing at the same time, and then you look at that arrangement of telescopes and deconvolve the Earth is curved; it's not flat. Yes, the Earth is actually curved and spherical, so you have to take that into account when you're actually doing VLBI arrangements. And so the VLBA allows you to have a much larger baseline of over about 5,000 miles at the best. Now, the Event Horizon Telescope goes a step further while trying to coordinate radio telescopes all across the globe. And the goal is to be able to see the event horizon, or see the shadow of the event horizon around the black hole at the center of the Milky Way. And they will start giving, in sometime later this year, later on 2018, will be hopefully the first images, and below we see a simulation of what they expect to see, developed by CFA at Harvard, Center for Astrophysics at Harvard, by Hotaka Shiokawa. So the Event Horizon Telescope at eventhorizontelescope.org, they're combining all sorts of radio telescopes together in order to see the radio emission at the center of the galaxy, which would be really fascinating once they get it going. All right. So interferometry gets radio images as close to the resolution as optical. So you have to use interferometry in order to get the resolution of optical telescopes. It's the only way to do it, because big telescopes like Arecibo and even FAST can't do it. So it's neat and everything, but you need the interferometry in order to get it. All right, so what can we see? Here's an example. We were looking at M87 before. There's its optical image. M87 is a really huge elliptical galaxy in the center of the Virgo cluster, about 60 million light years away, and we see it's an enormous giant elliptical, and it has a jet in the center. And this is a Hubble Space Telescope legacy image, and that previous image comes from the center CFH observatory down at Canadian France Hawaii telescope on Mauna Kea. So this is a great image by the CFH telescope. And this image is the Hubble Legacy Archive image of the jet coming out of it. But if we want to study with the VLA, we actually looked at this before, we see that the VLA itself can actually see the movements of the jet. And so we see that the jet itself is about 4,000 light years long in the radio. And in visible light, we see that this 4,000 light year long jet actually has knots in it. And if we look with the VLBA, we can see down to about a tenth of a light year. Tenth of a light year is a light month. A light month is 30 light days. How far is Voyager from the Earth? The spaceship launched in 1977 is about almost a light day out. So on the image in the center, taken with this NRAO image by Jay Beretta et al., and this we're looking at a couple of pixels across this image is the diameter between the Earth and the Voyager spacecraft. So that's really interesting. So some of the lumpy, tiny couple of pixel images is the size scale of that distance. So we're really seeing the motion of huge amounts of material being jetted out from something, some supermassive jet, some jet that's being formed, probably by a supermassive black hole. As material falls into the black hole, something happens, and we'll discuss what that is later. And so there's a much tighter view that the VLA took with a 4,000 light year diameter across, and there's 2,000 light years. But then we look at the inner tenth of a light year, and a couple of pixels on this image would be roughly the size of the distance between the Earth and the Voyager spacecraft that was launched in 1977. Today we continue with our basics of telescopes by talking about space-based astronomy. So last time we were talking about radio astronomy, which is basically ground-based because of the size of the facilities, but now we're going to be looking at things other than the ground-based observing and what's going on up in space. So why do we go up in space? It's because of the following. Well, first, you can get visible light on the ground and radio light on the ground, but you can't get infrared, ultraviolet, X-rays, or gamma rays on the ground, and significant numbers of radio can also not be gotten on the ground. But we're looking at things we can actually build and fly today, and this is what we're talking about. So again, why go up in space? Because the atmosphere is only transparent at a few wavelength regions, meaning the light can make it through the atmosphere without being absorbed or reflected or blocked in some way by the Earth's atmosphere. For very, very short wavelengths of gamma ray, X-ray, and UV, it's the ozone and oxygen that does it. In infrared, it's absorbed by water and carbon dioxide and methane. And way, way, way in the far radio, in the extraordinarily long wavelength radio, the radiation is blocked simply by there being high altitude electric charges way up in the ionosphere, so it really bounces off of them. All right, so there are two windows that make it down to the Earth: the visual light, which you and I use with our eyes, and radio, which makes it down to the ground. All right, so when we look at why we're going up into space, it's because ground-based telescopes are limited by what we call seeing. And seeing is simply the distortion of light as it passes through the Earth's atmosphere. As light passes through the Earth's atmosphere, it encounters very, very briefly tiny turbulent bubbles, really, really, really tiny turbulent bubbles. And they can range from the size of a few millimeters to maybe a couple of centimeters in size. And those things are bubbles that have independent temperatures, independent density, independent humidity, and that's enough to make the light refract. So all you have to do is have a change in temperature of a little bubble, and all of a sudden the index of refraction is a little bit different, centimeter to centimeter, inch to inch, and that deflects the direction of the rays of light, and therefore scattering them slightly, just the tiniest bit. And so that blurs the view. So resolution is reduced by simply having an atmosphere to look through. So if we can get above the atmosphere, we get rid of this thing, and maybe we can get to diffraction limited observing. And that's the goal of going up into space, is to get rid of the problem of seeing, or the degradation of the resolution because of the Earth's atmosphere turbulence. All right. One of the first things is, of course, we'll talk about a bunch of them, but let's talk about infrared astronomy. Infrared astronomy is the light that is a little bit longer than red wavelengths, so it's longer wavelengths, longer than, say, 8,000 or 9,000 angstroms, and into a few tens of thousands of angstroms into microns. So infrared telescopes can be placed aboard balloon-based things, such as the balloon-based observatory called BLAST and others. And they can also be flown into orbit. So let's look at a couple of those. And what does infrared look like? Well, if we look at foggy type views, meaning there's some particle in the air that blocks or absorbs the light, then a foggy view will actually go deep. It won't go very far. So it's either moisture or fog or smog or something that actually blocks the view. However, the longer wavelength infrared light can actually pass through that and pass through smoke. It can pass through larger molecules because it is longer. Its wavelength is longer than the size of those objects, so it's not affected by them. So infrared light will get absorbed by the atmosphere in the distance. And in fact, this infrared view does show that way off in the distance, in the far, far, far edge. It gets extraordinarily blurry because, well, there's kind of a distance fog as a result of the infrared not being able to get here from there. And that's because the infrared light is absorbed. But up until that point, it gets, if a few miles away, then the infrared light can travel relatively freely. So what can we see with infrared vision? Well, specifically the Hubble Space Telescope has been outfitted with a series of infrared detectors because it's up in space. And so the Eagle Nebula, which was first looked at, we called it Pillars of Creation, and now it was revisited by the final servicing mission of the Hubble Space Telescope, the Eagle Nebula, and they look very different between optical view and infrared view. The optical view highlights the warmest stars, the hottest stars, whereas the infrared view, you can see huge numbers of additional stars. And that's because there are many, 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 many more stars that are tiny and dim and cool. So they radiate primarily in the infrared, and they're not bright enough to be detected in visible light. So they're very dim and very cool and very red. So we can't actually see them in visible light. Also, we can see through much of the clouds that exist in the visible light. So the infrared again passes through dust, unless it's so thick that it can't pass through. Or the dust itself is warm, and then it emits light in the infrared by itself. Again, we see the same effect in the central region of the Orion Nebula, the M42 and Orion Nebula, which is by the Trapezium cluster. So if you look at the Orion Nebula, M42, and check that out on a winter night, you'll see 4 stars at the center of it, and those are called the Trapezium. In visible light, they're bright. You can see them with a moderate telescope. But in infrared, they're extraordinarily bright because, well, they're super hot, so they're going to emit a lot of infrared. But now we get rid of the effect of the gaseous element, which is seen in the visible light image. But in the infrared light image, we don't see the gaseous portion. We just see the dim, 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 tiny stars. So we see all these dim stars that are barely visible in the visible region of light, or visible, invisible, which is kind of a funny way of talking about it, but that's what we have to. But yet you see the reflection of the infrared off of the dust in the background as it warms it. So we get warm dust is also emitting light in the infrared. All right, so you have completely different views. Now you can get to dedicated infrared observatories. The Hubble Space Telescope has ultraviolet detectors, optical detectors, and infrared. But one of NASA's great observatories, part of their great observatory system, was the Spitzer Space Telescope. And the Spitzer Space Telescope was a dedicated infrared telescope, and it took enormously amazing images. We can see the difference between the visible light and infrared images on the right between the North American Nebula, which is part of the which is in the summer sky. And the visible infrared light will highlight dusty regions where stars are forming, and we can actually see it doesn't necessarily highlight the gas. So on the left-hand side, we see the pink glow of hydrogen gas, but on the right-hand side in infrared, we see the effect of dust. And so dust shows up as a bright image, but on the left-hand side, dust shows up as dark. On the right-hand side, we see dust glowing because of its cool temperature. And we also see the places where dust is densest and the various cool portions. We also see somewhere down in the center of the infrared image kind of a dusty area with some spots in it, and that's a denser area where the infrared light can't even get out, and that's where stars are being formed. So infrared light is perfect for actually isolating and checking out young star formation. In addition, we can show that with one of the classic things that the Spitzer Space Telescope team put together, with Mark Povich from Penn State. He showed that a specific series of images, this is a composite image from the Spitzer Space Telescope. We can see that the Messier object 17 with the southwest extension is a dark star-forming cloud, and that is on the right-hand side, and stars are forming inside of these dusty, dark bands. And so those are so dense that they don't even let light out, not even infrared. So those are cool, very cold, dusty things that might be on the order of tens of Kelvin in temperature. But we can imagine that it's actually a flow of dust and gas from right to left that takes millions of years because, well, it's very large. the distances are extraordinarily large and the objects are extraordinarily large in size, on the order of light years. So when we get to M17, the bright star-forming nebula, we see the brightest of things, the O and B type stars, illuminating the nebula after they'd formed. And so since the O and B type stars have formed, they are illuminating the gas and dust surrounding them, and that makes the bright nebula what we call the Omega Nebula, or the Omega Nebula is one of its names. And if we then think of the M7 as material that had flowed through, we see kind of a bubble sort of structure, and that may have been the result of a supernova explosion that happened after it flowed through a dense region. So we can think of this area as a dense region into which, from right to left, goes from not so dense to extraordinarily dense, again out to less dense. So right where the bright star-forming nebula is at is where things get kind of jammed up. And the idea is that this is a spiral arm of the Milky Way through which stars are forming. And we can use the infrared observing to actually find places where stars are forming and trace actually the evolution of stars. All right, so here's a kind of quick back and forth between M81 and M82 in visible and infrared. Visible and infrared, they totally look different. So they tell you completely different things about what's happening in those environments. The most important space telescope that's going to be coming online, which will be hopefully launched in May of 2020. It's many years behind schedule and extraordinarily over budget, but let's hope it gets going. It's the James Webb Space Telescope, named after James Webb, who was one of the more important people in getting the Apollo missions going online. And so the James Webb Space Telescope will be the next generation infrared telescope that will succeed the Hubble Space Telescope in about 2 or 3 years. The goal of this thing is to actually be the next generation space telescope. It's a really huge thing, and it'll live not in Earth orbit. It will not be serviceable. We do not have anything that can go out and service it. Maybe the Orion module, maybe that's an idea, but not right now. There currently is no way to be serviced. Unlike the Hubble Space Telescope, which was designed to be serviced, the James Webb Space Telescope is not. So there it is at its location at Goddard Space Flight Center being assembled. You can see it's an enormous structure, about 6.5 meters in diameter, and it's built up with a series of hexagonal mirrors made of beryllium with gold coating on it. That's where the gold is from. So this is a dedicated infrared observatory, because if it was optical, we might not want that yellow sheen on it, so we're really not worried about it. We're worried about infrared observing, and that's its main goal, is infrared observing. All right, so the James Webb's mirror is about 6.5 meters in diameter, which is about 3 times the size of Hubble's 2.5 meter diameter mirror. And if we look, we can see somebody inspecting it with a flashlight, and those guys are wearing suits so that they in a clean room. And let's just hope he doesn't drop that satellite or that flashlight. So the James Webb Space Telescope has been completed. It's going through checkout phases. It had a bit of a problem with one of its solar panels not opening, so that pushed back launch date to May of 2020. It's an incredibly expensive undertaking, and in some senses is kind of controversial because many astronomers think that it took a lot of money away from lower cost efforts in astronomy, and its price tag is going to be on the order of $10 to $11 billion after it's fully complete from its original design in 1996. So the James Webb Space Telescope is the hope for the future, and it better be right or a lot of people are going to be really pissed. And what is it going to do? When it's launched finally in May 2020, it'll go way out past, it was launched from Earth, that ring around the Earth. The green line is the Earth's orbit around the Sun. The gray line around the Earth is the Moon's orbit around the Earth. So it's going to go very far, all the way to about 5 times the distance away from 8 times the distance, or 5 to 8 times the distance between the Earth and the Moon. And it'll be at a location called L2, or the second Lagrange point, which is a gravitational balance point between the Earth, Moon, and Sun. So that's where it's going to live, and this is its process of getting there. Once it gets there, it will kind of float around in a like a halo type orbit. it'll be at this time that would be 8 times further, 5 times further than the distance between that humans have ever gone. So this is why it can't be serviced at all ever by humans. Now it's possible that a future spacecraft could be built and go out there, but there's currently no human spacecraft that can go out and fix it if there are any problems. So that's part of the reason why it's over budget, is that you got to make sure it's done right the first time, because that was what happened to the Hubble spacecraft, and that's what instantiated its need to actually have its first servicing mission a couple years after it was launched. So here's what will happen when it is launched. It gets launched inside a fairing, and then it has to unfold very gently. This unfolding is going to be done en route. So as it goes to its L2 location, each one of these processes, each step, the sun shield will be pulled out and drawn away at each level, and then after each sun shield is pulled out. And why does it have to have this sun shield? And the reason for that sun shield that's being created is so that it can actually block the light of the Earth, Moon, and most importantly, the Sun. And it'll always keep that shield between the Sun and the Earth and Moon. And in fact, it'll stay out of the shadow of the Earth and Moon in order to have a constant temperature profile. So that shield is specifically for that. After it's deployed the shield, it deploys the secondary mirror and then deploys the mirrors around, so it has a full appearance. So the heat shield itself is there so it can keep an extraordinarily low temperature. And that low temperature is critical for infrared observing, because if it didn't have that low temperature, it didn't have that heat shield, then the very temperature of the telescope itself, the instruments on board, just by the need of the solar panel electric generation inside it, would be simply too warm to actually detect the infrared light that people are hunting for. And the goal of the James Webb Space Telescope is to, of course, look at extraordinarily cool processes that are happening without using too much coolant. So what's it going to hunt for? Well, one of the important things it'll hunt for is exoplanets, or planets around other stars, but in order for the James Webb Space Telescope to actually see the most distant objects, such as the early universe, the goal is to see the first galaxies and the first stars, and to see that everything's redshifted deeply into the infrared, and Hubble simply can't see it. It doesn't have the proper filters, it doesn't have the proper diameter, it doesn't have the proper detectors, so it can't see the first galaxies. You can get really close, but it can't see them. So the James Webb Space Telescope should be able to see the very first stars that ever came into existence in the deep history of the universe. Alright, so now after we think about infrared astronomy, we go to the other side and go to ultraviolet, shorter wavelengths than blue, and ultraviolet images are very different. We're looking at extraordinarily hot processes, things that are something that's created extremely energetic light. This is the same light that gives you a sunburn on a summer afternoon, and we can see a couple of things: supernova remnant, which was excited by the shock waves of the gas moving from the supernova remnant through the interstellar medium, as well as the hot stars in M81. Here we have a better depiction of that. And the ultraviolet satellite GALEX, the Galaxy Evolution Explorer satellite, surveyed the skies for about a decade and looked at many things in ultraviolet light. And if we look at the comparison between the Galaxy M81, which is about 10 million or so light years away, we see that there's lots of star forming region happening in the disk of the galaxy, and even there's a little star forming region off to the left hand side that we don't see in visible light. So in ultraviolet light, we see that there's lots of O and B type stars forming furiously inside that galaxy. Likewise, the Caltech group, actually, after the GALEX was NASA was done, they said, we don't know, we got a perfectly good satellite, but we don't know what to do with it anymore. Maybe somebody else wants to run this thing. And so Caltech said, let's do an incredibly detailed survey of the Andromeda Galaxy. So they used the GALEX to point at it for a very long time and create an enormously detailed view, a high resolution view, deep view of the Andromeda Galaxy. And the Andromeda Galaxy is supposed to be a spiral galaxy similar to our own, but you can see actually from this image it looks more like a ring galaxy. And all of the bright spots that are in there, not the yellow spots, those are stars that are close to us in our Milky Way. This is about 2.5 million light years away, and we see that this object, which is the Andromeda Galaxy, contains huge numbers of hot stars in star-forming regions. And they're kind of in a ring structure. Not really a spiral structure, more like a ring. So that kind of mirrors what is seen by the infrared telescopes as well, and we'll see that soon. Likewise, GALEX was able to see something really interesting, a variable star called Mira, which is a prototypical variable star. They're called Mira variables, and it's an asymptotic giant branch type star that's on its last legs. But Mira is actually traveling relatively quickly through the interstellar medium. Its speed through space makes it look like it's having a cometary tail going behind it. So since it's an aged star as an asymptotic giant branch star moving quickly through the interstellar medium, we see there's a bow shock in front of it, we see there's a cometary sort of type of tail, and this is just an individual star many tens or hundreds of light years away. And the ultraviolet light is happening as a result of the ionized gas that's still emitting the light from the star. So the light from the star ionized the gas, and as it some of that ionization that you see is coming from the fact that the gas itself is moving extraordinarily fast and slamming into other gas in the interstellar medium, and thus creating ultraviolet light. But the bow shock area, that's also collisionally based, because it's like plowing through the interstellar medium. But the brightest spots are, of course, the star itself, radiating huge amounts of ultraviolet light, which then comes to us from that we can see with the Galaxy Evolution Explorer ultraviolet satellite. All right, the next variable thing we go is, let's go shorter wavelength still into X-rays. Now, X-rays and gamma rays don't reflect off of mirrors like primary mirrors that we see in optical telescopes or the James Webb, or just the type of telescope you go buy at a photo store. No, you can think of them as more like an X-ray will skip off of a surface, but it won't reflect if it's normal to the surface. So you have to make these things nested. So if you wish to detect X-rays, you have to gently redirect them, which means that the mirrors look really strange. They look like nested things, nested rings. And so that's the design of most X-ray observatories. And one of the most recent ones is the NuSTAR, or a NuSTAR satellite, which's goal is to look at extraordinarily high energy X-rays. And you can see that the structure of this satellite's a little weird, because of this long gantry and this thing at the end of the gantry, and the telescope, the detectors are down by the solar panel. But the thing at the end of the gantry has a whole bunch of nested rings, and those nested rings gently change the direction of the incoming X-rays. And as they do so, they focus them about 30 meters down the way. So when this was launched, it was actually launched from a rocket on board under a plane, and then it went up to orbit. And this rocket then deposited where it is, and then the gantry extended, and they went through a series of outfits. And so this was really interesting. It's like a telescope without a tube. So NuSTAR is able to see some amazing things. Its goal is primarily to look for high energy X-rays, but this is an image of the supernova remnant Cas A. And so we see in the foreground a series of visual image overlay of stars in that field, but the glowing cloudy thing is the image taken by the NuSTAR telescope, and that comes from X-rays that are emitted by material that's plowing into the interstellar medium at extraordinary speeds and heating it up to X-rays, which then glows. And this is from a supernova that was detected, that was seen over 300 years ago in the night sky in Cassiopeia, and possibly was even seen by William Shakespeare himself. Fascinating. All right, so one of the longer running X-ray observatories, also part of NASA's Great Observatories program, is the Chandra X-ray Observatory, and that's been running for a long time out of Harvard. And it's an enormous structure that was launched by the Hubble on board the space shuttle, and it too takes lower energy gamma X-rays than NuSTAR, and we can see the same image in X-rays from the Chandra X-ray Observatory of Cassiopeia A. And Cassiopeia A is a Type 1A type supernova, and there's all sorts of interesting things happening in it. And so the analysis of these high energy packets of light is what tells us things about what's happening in the sky. So let's take a quick look. Here's a visible light image that I took using a telescope of the Andromeda galaxy. There's a visual taken from Astronomy Picture of the Day. Here's the same image of M31, the Andromeda galaxy, taken infrared using the Spitzer Space Telescope. There it is with the Galax Observatory that we saw before, and now we're seeing the core of it in X-rays with Chandra, and we see the center of it is actually a series of spots where we think there's a supermassive black hole in the center of that galaxy. Now we go up to the highest energy of light, which is gamma rays, and they can't be focused at all. They won't skip off of anything. They simply get absorbed. So when they interact with matter, they interact hard. So it's very hard to focus them, so you have to use other kinds of techniques to focus them. And one of the other major great observatories other than Hubble, Spitzer, and Chandra was the Compton Gamma Ray Observatory, which was launched in 1991 when I was an undergraduate. And it observed for about a decade until it was plunged into the ocean. And its goal was to observe the sky in gamma rays, and its map of gamma ray bursts still is being used today. Compton Gamma Ray Observatory was succeeded by a number of other gamma ray observatories. This is the Fermi Space Telescope, which looks like a big old refrigerator box. And the Fermi Gamma Ray Telescope in the sky detects incoming gamma rays in a similar way that the Compton Gamma Ray Observatory did. It has these kind of what are called calorimeters, which when a gamma ray comes in and hits these things, basically hits a series of foils, and eventually it hits an electron or interacts with an atom, and the gamma ray then converts into an electron-positron pair, or an electron and an anti-electron. By the gamma ray interacting with matter turns into matter and antimatter, which is really interesting. And then the direction and energy of the electron-positron pair when it gets deposited inside of the calorimeter at the bottom. It's not even a telescope detector, it's called a calorimeter. That tells us the direction from which the gamma ray came, as well as the energy of the incoming gamma ray. So this is Fermi's 5-year all-sky map, a total map of all the gamma rays it's detected in 5 years. And you can see that the Milky Way, the band of the Milky Way goes across the middle. There's some prominent features. Some of the more prominent features off to the right-hand side are from pulsars. And most of the spots that you see around are either active galactic nuclei that are extraordinarily distant, but the center of our Milky Way is a gamma ray emitter as well. All right, so the Fermi and Integral Gamma Ray telescopes actually served an amazing purpose on August 17th of 2017. They actually confirmed, were the first things that showed a light image, an electromagnetic counterpart to a gravitational wave detection. The LIGO Virgo group detected a gamma ray, detected a gravitational wave in both the LIGO observatories, and the absence of which in the Virgo observatory in Europe actually showed where it was in the sky. The Fermi detector looked and saw something 16 seconds later, and the Integral also detected a gamma ray burst, a burst of gamma rays 16 seconds afterwards. So there was a burst of gamma rays that occurred after the gravitational wave, and this heralded the collision of two neutron stars. So basically a burst of additional 500 gamma rays in about a second or two, each second for a few seconds, is what heralded this cataclysmic collision of two neutron stars about 1 billion years ago. It took a long time for the light to get here from there. Now, we're doing space-based astronomy, and we can't ignore the Kepler Space Telescope, which is an optical observatory, and it's a space-based observatory. Its sole goal was to find planets around other stars, and it's found about 3,000 or 4,000 candidates for stars, with many hundreds of others confirmed, and a handful of Earth-sized planets around Sun-like stars. So it's been an amazing success. It's one of the most important things that has radically changed astronomy by a space-based observatory that stares unceasingly at a patch in the sky. And it lost 2 reaction wheels a few years ago, and so now it's kind of drifting around, but it's being used anyway because it's still an amazing photometer. It's one of the most sensitive things. You can see a light bulb turn off in Times Square is how sensitive it is. And so its use is amazing. We'll talk about exoplanetary exploration later, but you can't underestimate the importance of the Kepler Space Telescope. And because it has just launched a month ago, This is May of 2018. A month ago, the Transiting Exoplanet Survey satellite, a test satellite, which sole goal is to do a full sky map of local Earth-sized planets in the solar neighborhood. So it's not going to be able to look at bright stars in our neighborhood, but it's going to detect a lot of them. So its goal is to look for Earth-type planets and super-Earth, which are like maybe 1.5 to 2 times the size of the Earth, and they're close by because it can only detect stars that are nearby. It's a bright star looker, whereas the Kepler Space Telescope can see things up to about 3,000 light years. Everything, or 6,000 light years, somewhere in there. The test survey is designed to be only in the local solar neighborhood. And part of the reason for that is to provide a map or a survey so that when the James Webb Space Telescope goes up, it can do follow-up. And the goal of follow-up is hopefully be able to do spectroscopy on those planets that TESS finds. And if it finds planets, that would be fantastic. And it will. It's going to find a bunch of them because one of the most important things at Kepler is that every star in the sky has planets, no matter what. So when we look at space-based observing, it's been a revolution in terms of what we've learned, and so going up into space has changed pretty much everything. You can't get too much on the ground, but with Hubble Space Telescope, James Webb, the X-ray observatories, the Spitzer Space Telescope, Kepler, Fermi, Spitzer, numerous other objects, and hopefully with this James Webb being launched in May 2020, there will be even more things being discovered. So space-based observing is clearly is incredibly profitable in terms of the science, and it is the place where we have gotten enormous return on investment in terms of understanding what is going on in our universe. And most of the things you will hear in any astronomy course are a result, the physics that underlie the astrophysics come as a result of looking at space-based astronomy. So there it is, and it's an amazing time to be alive and see what is happening up in the sky. This one will be an interesting one because it's looking at the entire sky. So what we do sometimes in astronomy, and in fact it's not just taking individual pictures, sometimes what we want to do is we want to take an entire survey as much as possible of the entire sky. And that shows us what's in the sky, just like making a map of the Earth back when people were doing major exploration. Making a total map of the sky is also one of the most important explorations that we can do. So we see here a series of small images that show what the sky looks like in various wavelengths, and the information gathered by looking at all these various wavelengths actually tells us incredible amounts of information about the nature of the cosmos. So let's take a look at the first thing and remember that we're looking at the full sky. So this is called an ATOF projection, and it takes the surface of a sphere. The Earth is spherical, it's round. Oh my God, did I have to say that? It's round. And then what we do is we project it onto a two-dimensional surface. It is a round thing. There is no flat Earth. Anybody who says so is quite crazy. In any event, what we do is we think that the edges go linking up. One of the edges links up to the other edge, and you can imagine it been sliced at the far side and they actually projected around so that they actually are maneuvered around. So what we're looking at is we're going to be looking at a similar projection of the full sky. So if you go off the right-hand side, you come on to the left. If you go off the left, you come on to the right. But if you go to the top, you do not go to the bottom. So it's only a left-right cut. All right, so the first thing we'll look at is an amazing pastiche of pictures that was put together by Axel Mellinger, and this has been preserved at the NASA Goddard Space Flight Center's Lambda data set, which is a place where they take all sorts of amazing images. So Dr. Mellinger took a huge number of ground-based observatory images and stitched them together for a full sky image. And you can kind of see that in this image that look kind of stitched together because it was made by numbers of different observatories. You can see that there's some slight color variations across it. But the most important thing that we see is that this is visible light, and it's a color visible light image. He tried to balance them out so they're the same rough color. Across the middle, Now, typically for all of these surveys that we're going to look at, we're going to look at them from the galactic plane. So going across the middle is the Milky Way, and directly in the center is the center of the Milky Way. So this is not according to the sky, according to how fixed positions such as the equatorial coordinate system based on the Earth. No, this is a coordinate system based on the plane of the Milky Way, which is the most natural thing you see in our sky. So because it basically makes a line, so why not keep it that way? So we see that in the invisible light, we have some certain features. Directly in the center is the center of the Milky Way, which is a collection of billions upon billions of stars. And surrounding that are some dark, dark, dark patches, which is dust blocking the light. We also see some pink glows that tend to be more centered roughly on the plane of the Milky Way. That's hydrogen gas and star-forming regions. Down into the center lower right, we see two sort of bright patches. Those are the large and small Magellanic Clouds. And off to the left-hand side, about halfway out the side, almost two-thirds of the way out from the center, on the left-hand side is a bright spot. That is the Andromeda Galaxy. So anyway, we see Orion off to the extreme right, but basically the major colors are stars, gas, which is the pink glow, and dust, which is the dark things that absorb light. Amongst that is also above and below the plane will be galaxies and other stars that are close to us. So that's kind of our view of the sky in the optical view. Now we can look at specific wavelengths of light. One of the more important optical wavelengths of light is hydrogen alpha, or 6,563 angstroms, or 6563 nanometers, and 656.3 nanometers, I should say. And this is H alpha, which is the glow due to hot clouds of hydrogen gas. And we'll go back and forth between H alpha and the optical image, and you can see the patches where the H alpha is bright, and again it's centered on the center of the plane of the Milky Way. And H alpha glows because some very, very, very hot stars are in the presence of hydrogen gas, and so they ionize that gas, and as the gas recombines, it glows in specific wavelengths of light, and one of them is H alpha, and that is the pink glow associated with hydrogen. And we can see that H alpha map is very patchy, and that's because we're looking at patches of hot locations across the Milky Way. And the C-like structure on the extreme right in this image, that's the Barnard's Loop, and it surrounds the Orion Nebula. And the Orion Nebula is the upper right of the two spots inside of that C-like structure. So there's massive structures that are off to the left, which is, I believe, the Rho-Fucus complex, and other structures that delineate star-forming regions. We can even see the Large Magellanic Cloud off the Milky Way down to the lower right, a lower portion to the right, about halfway out, and some other things that are very high up as well. In any event, that is H alpha is a result of star-forming regions and hot ionized gas, and this is, of course, from Finkbeiner, who's worked with large numbers of surveys of the H alpha. There's three different sets that we're talking about: WHM, WHAM, VTSS, and CHASA, which were massive H alpha surveys from the ground. All right, this is another view of that, just looking at the center of the image. And it's kind of spread out, so we're only looking at the key critical things, and it's a slightly different view. Instead of an ATOF projection, it's a projection that shows just the dominant events in the Milky Way. Centered again on the center of the Milky Way, we see a bright spot. So there is some star forming that does occur, but in general, most of the star forming is not towards the center of the Milky Way, which is another interesting discovery. All right, so the next thing we'll do is that there's dust, but we saw originally in the optical view that there was gas too. Well, there's not just gas, but dust. And so if we look at longer wavelengths of light, meaning micron wavelengths, which are 1,000 times longer than nanometers. So we're looking at, this was done by the Wide Field Infrared Survey Explorer, the WISE telescope, one of NASA's major space-based observatories, and it looked in numerous infrared bands. And what we see going across there is that we see a tight band that goes across the middle that forms the plane of the Milky Way with a strong amount of brightness towards the center. The colors are specific to infrared light, so this is a false color image, just like the H alpha was also a false color image because it's only one wavelength of light. The false H alpha is only one wavelength of light. So what we have here in this image is just simply variations of brightness. So red here is very, very bright, blue is very cool. Well, cool meaning not much light is coming there. So we say it's dim. So blue is where it's dim, red is where it's bright. And that's only in one wavelength of light. However, if we then go forward and look at this infrared image, we actually have composed it out of three different wavelength bands. So we can approximate each by a color. So the blue-green or the cyan is stars and galaxies. So those would be starlight in general. The deep green will be dust and gas, will be mostly dust. So the green and red will be dusty emissions. So we can see that the blue, which goes in the center, since that's starlight or galaxy light, that's very tightly confined into the disk of the Milky Way. But the green actually has a puffy structure, and that puffy structure arises because, again, dust is associated with star-forming regions, and unlike the optical image, the infrared image of the blue that shows the starlight is not impeded by the dust, so it travels through the dust, and we can see the light of the collected stars in the infrared image. It also shows us that when we look towards the center of the Milky Way, we see most of the stars. And you can also still see the bulge at the center, which is a halo of stars, but the brightness of stars is pretty much confined to the disk in general. So the green shows where the dust is, and that corresponds to star-forming regions again. So dust here means particles that are warm, that are about the same size as cigarette smoke dust. So they're extraordinarily tiny objects, and they're many thousands of molecules in size. And so they're really kind of small objects. That's what we mean by dust. And the dust is not much bigger than cigarette smoke. All right, so let's look at longer wavelengths still, and this is in microwave wavelengths, and these wavelengths will be on the order of millimeters to centimeters, whereas infrared is on order of microns, which is 1,000 times smaller than a millimeter. Now we're looking in millimeter and centimeter wavelengths, and this is microwave region, and this is a map that's made by European Space Agency's Planck telescope. And the Planck telescope its goal is to search primarily for the cosmic microwave background, which you can see above at the upper left and the lower right. But it also detects very strongly the Milky Way. So the Milky Way itself has huge emission in microwaves, and that comes from the dust and gas, mostly the dust, and also the galactic magnetic field actually causes the emission of this as well. So mapping the galaxy's emission in microwaves is extremely critical to understanding the cosmic microwave background, because the galaxy emits a huge amount of microwaves. So in any event, we see again the galactic center and the galactic disk going across. We see these huge cirrus-type clouds which go above and below, and they're very loosely surrounding the star-forming regions. Though whatever is emitting the microwave emission is usually it will be associated with dust and gas. It's extremely cooled processes, and so these will be this emission comes from essentially gas and dust again, which is very, very cold, and being influenced by the magnetic field of the Milky Way. All right, so let's then take it even longer, one of the more longer wavelengths of light in terms of radio. So microwaves get into the short end of radio frequencies. Now we're going into the full radio frequency, which is 21 centimeters, or about the length of a piece of paper, or the width of a piece of paper. And 21 centimeters is the wavelength that neutral hydrogen, or a hydrogen that is not in molecular form like two hydrogen atoms together, but a single hydrogen atom. And what's happening is that across the Milky Way, occasionally the electron in its orbit flips from being spin up to spin down, and it's an extremely low energy emission. And this very, very, very low energy emission is in the wavelength of 21 centimeters. So this map, where again, well now here, because it's at a single wavelength, we're again looking at the blue would be where it's not very bright, and the red is where it's very bright. And so it goes from blue all the way to red to show dim to bright. And so in the plane of the Milky Way, we see that the neutral hydrogen is strongly confined to the plane of the Milky Way. But we do see those cirrus clouds above and below, just like we see in the microwaves. So there is some, even though so what we see in microwaves is additional wavelengths of light that are being emitted by clouds of gas that also emit in radio frequencies such as carbon monoxide, methane, and other simple molecules. But the neutral hydrogen is really the thing, because that's the thing that says stars are formed out of hydrogen, so this is a big thing. This was done over a very long period of time using the Parkes radio telescope, which is part of the Australian government, and so there's the key there. And this is also this has been put together by and is held by the Lambda at Goddard Space Flight Center with NASA. So this is a full sky image again of the neutral hydrogen, and we see it's confined to the Milky Way, but we see two bright spots down to the lower right, below and to the right. Those are the large and small Magellanic Clouds, which are neighboring galaxies or orbiting galaxies of the Milky Way, and there's active star forming region going on in both. So neutral hydrogen is where it's happening. Now, if we go even longer, almost instead of 21 centimeters, but 3 times longer, almost meter-long wavelengths of light, the Max Planck Institute at this particular wavelength of light, 400 megahertz. Now we're always talking the wavelengths we talk about FM and AM transmission. We talk about the so and so megahertz on your FM dial and so forth. But this is a 73 centimeter wavelength map of the Milky Way, and it's less and less and less resolved, because the longer the wavelength, the larger the aperture you need in order to resolve it. So the resolution is getting poorer as we go to longer wavelengths. But we can see again still that high cirrus cloud that seems to be coming up from the center of the Milky Way. But there's also lots of radio emission, and again, this radio emission will be due to cold gas clouds, and the gas will be tracers of things like of molecular clouds. And so we have these cirrus molecular clouds that are infused with hydrogen, but mostly towards the center. And the radio emission from the center is dominantly due to the magnetic interaction that the center of the Milky Way has on its surroundings. We can even go longer wavelength, and this is almost 10-meter wavelength. This is extremely recent data. This is from the previous data comes from the Max Planck, the All-Sky Survey. This comes from the Max Planck Institute, and it was done a long time ago. And this has been cited many hundreds of times as a full survey of radio emission in the galaxy. So please check out that info. It also appears in the Lambda organization, as well as the link below. But this one is from the LWA1, which is a low-frequency sky survey. And what's interesting about this is that this wavelength of light has never really been explored before. So when we look, and this is now a slightly different view, it's based out of New Mexico, and so they can't actually get a full sky image, because there's only one array, and it's in New Mexico, so they lose much of the southern sky. And so here, instead of it being a galactic map, it's now an equatorial map. And what we see is that the galactic center or the galaxy is actually this kind of hoop-like ring that goes across. And this is their map, so I'm not going to spend the 20 hours that it would take in order to reframe this image into a galactic map. It would be kind of painful. But what we do see is that the loop, which is the Milky Way, the bright spot of the loop on the right is the center of the Milky Way, and we see some other really bright spots. So this survey of extraordinarily low frequency, which would be, who knows, like vibrational frequencies or rotational frequencies of large molecules in the Milky Way. But you can see that cirrus sort of cloud that's on the right-hand side, and possibly even what might be bright spots that might be associated with star-forming regions. In any event, you can go to their website, which is the LWA1, in order to learn what this science is. And this is a fully operational telescope, and they actually broadcast everything every 30 minutes. So it's kind of funny. really low energy and low power, so they've decided to kind of make a radio transmission of low frequency observations of the sky. And you can see Jupiter going across their live transmissions, as well as you can see the sun. You can see it move, the sky moving. It's kind of cool. So it's very interesting full sky images of radio transmission being broadcast to you from New Mexico. So go take a look at it. Anyway, let's go to the other end of the side. So we looked at the very, very, very longest wavelengths of light. Now let's look at the shorter wavelengths of light. And here on the right, we see the X-ray emission that was seen by the Rosat satellite. And so the Rosat satellite looks in X-rays. And so instead of measuring this energy, the wavelengths in, say, nanometers or something like that, we're measuring in wavelengths that are so small that we might as well use the energy of the photon. And that's what they do. And that's why they said these three bands, which is the red is 0.25 kilo-electron volt, green is 3/4 kilo-electron volt, and blue is 1.5 kilo-electron volt. And why they do that is because that's the nature of the detector. The detectors really can receive or detect energies of X-rays. So that it's basically the detectors are different. And since the detectors are different, they quote their wavelengths different. In radio, we tend to talk about frequency. In visual and infrared, we talk about wavelength. But when we get to higher energy wavelength of light, we just describe the photon energy itself. So it's kind of funny. We can look at this. We'll look at all that in some other things too. But the electromagnetic spectrum is their equivalent things. You can certainly do this, but it's more convenient to say 1/4 kilo-electron volt than say a sub-angstrom level wavelengths. So what we see here is we see the band. Now we're back to a galactic map. And we see a bright spot in X-rays off to the right. That's probably a pulsar. I believe that might be the Geminga pulsar. But we see the X-ray emission from that bubble, which appears to be over the center of the Milky Way. We have other bright spots of X-ray emission. But here, instead of it being red means hot or bright, and blue means cool or less, here, if you have a color, you have something. So black is simply where you don't have data. So dim or black is where there is no data. So it's fascinating to think that the higher energy wavelengths of light seem to be coming from the Milky Way band itself, and the lower energies are diffuse from the background of light that comes from outside. And so that diffuse X-ray emission, that red diffuse X-ray emission, is mostly extragalactic. It comes from the diffuse background of galaxies in galaxy clusters and center that are extraordinarily distant. But we look at the higher energy X-ray emission, and that comes from the center of the Milky Way and along the plane of the Milky Way, and that probably is from pulsars and black holes. So let's go even higher energy into gamma rays. And gamma rays are being observed by the Fermi Gamma Ray Telescope, which was formerly known as GLAST, G-L-A-S-T, but they renamed it to the Fermi Gamma Ray Telescope. And this is an all-sky view of approximately, I think this is a 5-year data set. And so taking 5 years worth of data from gamma rays. And this particular thing, again now, because gamma rays are so difficult to detect, they would rather, this is where blue is, the darker the blue, the less the emission, the brighter the red, the more the emission. So here we see the Milky Way center is extraordinarily bright. The Vela pulsar, which seems to be the thing that we've seen left and right throughout here, that's a pulsar emitting strongly in gamma rays. The Geminga pulsar, which is only visible in gamma rays. The Crab Nebula, which is visible in gamma rays. And then you've got this funny thing is blazar, and that is looking down the barrel of a jet, of an ultra-relativistic jet coming out of a supermassive black hole some billions of light years away. So one of the brightest sources in the gamma ray view of the sky is something that's billions of light years away. We're looking straight down the center of the axis of a supermassive black hole that's spinning and materials falling into it, emitting gamma rays, and we're seeing it billions of light years away. But the Vela pulsar is fascinating because it's bright in many wavelength regions, and it's a nearby pulsar that was formed maybe about 3,000 years ago, or maybe 10,000 years ago. in a supernova explosion. So these pulsars, these recent pulsars like the Crab, Gaminga, and Vela, are things that are a result of recent supernovae. The Milky Way center, though, that emission comes as a result of the dominant, brightest spot in the center of the Milky Way. There's actually a supermassive black hole there, too. So when we look at gamma rays, we're looking at either the emission due to extraordinarily hot processes on the surfaces of pulsars, or material getting to become millions of degrees in temperature and falling into a black hole. And gamma rays can also be bursty. And this gamma ray telescope is showing the sum of all of it, but one of its main missions is to look for bursts, meaning some things that last for seconds only. And those are gamma ray bursts which herald the death of stars. So some of the tiny, tiny, tiny singleton spots throughout this map that are dim and blue are as a result of simply gamma ray emission from gamma ray bursts. And those tend to be distributed equally across the sky, and those are from the supernovae of ancient stars that may have exploded billions of years ago, and the light finally arrived to us in a very short burst of only a few photons. So what do we get? So astronomy can be done in many wavelengths across all the sky, and they're radio, infrared, visible, ultraviolet, X-ray, and gamma ray. We didn't really look too much at the ultraviolet sky, but that's with the GALEX observatory probe, and it's really, they have a very small aperture, so it's harder to make a full sky map of that. But radio light penetrates dusty regions. It can be used to study magnetic fields, interstellar clouds of gas and dust. The good thing about radio is you can make it just like the guys in New Mexico with their ultra long wavelength. They don't care if it's cloudy or rainy, just so long as cows don't come in the pasture and kick over the arrays. So they've got some really big cattle fences around it. Infrared, you need to be in space to get full sky surveys like the WISE spacecraft or the Spitzer spacecraft, because the Earth's atmosphere absorbs that. Visible light, we can put telescopes anywhere, and we can put them up in space, and that'll help us to make maps of the sky, and we get to see stars, the structure of the universe, and light from gas clouds. Ultraviolet light must be from space as well, and that comes from extraordinarily hot stars, young hot stars like O and B type stars, as well as hot gas clouds. And X-rays come from neutron stars and black holes and active galactic nuclei, and gamma ray observing is from extraordinarily violent processes on the surfaces of neutron stars, as well as active galactic nuclei and hypernovae and supernovae. One of the most interesting things that is coming up online soon is the Large Synoptic Survey Telescope, or LSST. So I invite you to go look at that. It's currently under construction and should be done within a year or so. And its goal is to take hundreds of panoramic images across the night sky every night. And so the camera that they're building is one of the largest cameras, and they'll have so much data that it'll be impossible to study by an individual. So they're part of the LSST's mission is to get the data out into massive online capacity so that people can look at it. So basically it's a 6.7 diameter primary mirror, but there's a big chunk that's taken out of it for the secondary, because the secondary it has to reflect to one of the largest cameras that's ever being built for an observatory. The goal is to be able to do things that are extraordinarily faint and be able to detect changes of position and brightness. So they're going to discover lots of variable stars, lots of comets, lots of asteroids, deep things in the outer solar system, things past Pluto, and see what the Oort cloud might look like. But it'll also be able to show changes in local nearby stars. And all of the exposures will be done over 30 seconds a pop. And so this camera, this 3.2 billion pixel camera, is going to record the entire visible sky twice each week. So this is going to be an enormous undertaking, and their public outreach is incredibly important, because they want you to go look at it. So this will be one of the greatest observatories when it gets built on the ground, because its goal is to get the data to people. It'll transform the nature of optical astronomy in about a decade or so, and that's its goal.